Welcome back to day two of the Bourne Symposium, number 32. I guess it's 32 and a half because we're halfway through it. A whole bunch of exciting talks. I think everybody either has a copy or things on their digital version. If you skim through these things, you can see how exciting this has been. And I just want to remind everybody that we will have very soon, if not right now, all of the mini papers on the website. If you have a concern about having your paper on the website, please tell Betty. But she's gone through and cleaned them all up because, like all of you, I'm not terribly good at actually following directions and putting things in the right places. So she's gone through and done all of that. They look fantastic. It is a really great way for us to capture all of the information. And remember that while it's not a peer-reviewed paper, it is still great literature. So be sure to put it in your resumes, even if you've done 3 or 4 or 5 of them. It's perfectly reasonable. So thank you to those of you who've spoken so far. We look forward to those of you who are going to speak. I know that there are other things going on today, but please stay for as much as you can. We have a lot of really exciting presentations. Thank you.
With that, we can start our first session of the day, and we'll first be hearing from Emily Blackwood on sightseeing archaeological features on the north coast of Peru.
Okay, hi, I'm Emily Blackwood. I'm an interdisciplinary PhD candidate. I'm an archaeologist. And the part of my research that I'm going to talk about today involves creating 3D models from cultural materials from archaeological sites on the coast of Peru. So before we get into that, I just briefly wanted to go over what archaeology is so that we all have an understanding. So it is the study of human activity through time, but how do we do this? So we analyze evidence left behind in spaces that were used by humans over any interval of time, from single use to extended occupations. In doing so, we are able to look back in time to visualize narratives of how past humans interacted with those spaces, how they solved problems, the types of tools they made and used, and what purpose they built their structures for. So today I'm going to focus on one of the sites that we had the privilege to visit and collect data from, the other that you will hear about from Kelly Hoover in a few presentations. So this site is indicated here by the red star. It is known as the Ostra Collecting Station, and it has been radiocarbon dated to 62 to 6,500 years before present. It's located on the north central coast of Peru, and as the name implies, it is a shell heap site that consists of a lot of oysters. So the radiocarbon dates overlap with the radiocarbon dates of an associated site that is about 5 kilometers to the south, known as the Ostra Base Camp, and is indicated here by the white star. The Ostra Collecting Station itself is in an interesting position and has some rather curious things going on. So it is located at the top of a sea cliff at the edge of an ancient shoreline, which is still visible and dates to the same age as the site. We know this because of Keone shells were covered along this shoreline, found in living position at the base of the site with radiocarbon dates that align with the radiocarbon dates of the site. So if we zoom in a little bit closer to the site, these 2 lines here are piles of what we call sling stones that appear to be set up as defensive measures for the site. Most are round, fist-sized rocks that are grouped in piles as shown here on the right. The southern line extends from a structure at the top of the site indicated by the red star, and the northern line is about 180 meters away. We are dating these piles using OSL, and if they prove to be the same age as the site, they will provide evidence of this site being the earliest instance of warfare in the Americas. So in between these 2 lines of sling stones, we have found 17 pebbles that are either incised or incised planed or planed. An incised planed pebble is shown here on the left. And what makes it incised are these carved lines here at the top. And planed means that the point was just kind of sanded or flattened down. These pebbles are unique to this site and its associated base camp site and they have not been recovered from any other site in America or South America. These pearls come from a disturbed context at the base camp that was looted in antiquity. Pearls are small and shiny and valued by humans even thousands of years ago. What's special about these pearls is that, to the best of our knowledge, they have not been recovered from any other archaeological context in Peru. So I know this is a bit blurry, so bear with me, but it's the best that Google Earth has to offer when you really zoom in on a site. And it exemplifies why good visualizations are needed. So first, this dark cluster of rocks, more clearly shown here on the left, extends from a 9 by 8 meter granite stone structure that has collapsed within itself. For a bit of orientation, this 1 by 1 meter unit is located in the top right corner of the structure, and this red arrow is pointing to the cluster of rocks that extends from this structure. The size of this structure is of note here, as this is considered large for this point in time. So a quick recap, we have an ancient shoreline, we have sling stones, incised pebbles, pearls, and a 9 by 8 meter granite stone structure. So all of these taken together provide a really great opportunity to create models for a potentially really important and interesting site. So now that I've set the stage a bit, I'm going to take us down to ground level. For my dissertation, I'm using virtual reality as a platform to visualize archaeological sites. As you might be able to imagine, these spaces are quite large, and it would be both labor and storage intensive to capture every angle of an entire site. So in using a bit of game theory, we decided to target specific areas of the site to capture what I wanted to highlight in the simulation. This is being built in Unity, and it's a really great way to showcase VR. So the areas to highlight are the sling stones, the structure, and two different areas of shell heap densities, one with light shell surface scatter and one with heavy shell surface scatter. So last summer, we were able to access the site so that I could create these 3D models. To do this, I wanted to try using two different ways of using photogrammetry, so with a GoPro and with a smartphone app, as well as using some LiDAR to see how well they would work in the field and how efficiently they could be used. So I was very fortunate to have the help of Kelly Hoover, featured here, who walked like not thousands, but a lot of miles, a lot of miles, holding a GoPro on a painter's pole to collect all these photos necessary to create one model of an area while I was working in another area using an app to do the same thing. As you can see here, Kelly is quite tiny in the background and is walking one length of a grid, which once she reached the end, she would turn around and walk back down the same length until the grid was completed. All of these images were then stitched together using Zephyr 3D Flow to create a 3D model that I can use in my VR simulation of the site. These images are geo-referenced, so I can import it right into Unity, which is the program, again, that I'm using for my VR simulation, and overlay this model with the digital elevation model we already have of the site. Here is the structure. Again, this is the dark cluster of rocks, just for a little bit of reference. So the other way that I was creating these models is through the use of the Polycam app. Shown here on the left is a video of the process in the field, and on the right are two images of the setup. So I used a white pillowcase as the background, a Lazy Susan to rotate the artifacts, a tripod with a smartphone rig, and a light attached to the top, all positioned on a mouse pad for stability, as this was done in the back of a truck in the field. The video on the left, I am capturing images of a sling stone. Each capture took about 60 to 70 images to be successful. So here on the left are three different examples of sling stones. I wanted to see if the app could capture different rock types that had different colors and different textures. To the right is an example of a unifacial stone tool, so a tool that's only been worked on one side. And the furthest on the right is not an artifact, although it looks like one. It is a ventifact, which is a fancy word for a rock that has been worn down by wind and sand. I wanted to include examples of non-cultural materials as well, because they are present on the site and are used in my simulation. The bottom center is an example of an oyster that has been recovered from the site. The bottom right is an example of when a capture fails, which is disappointing because this can take about 10 minutes in the field. It then has to process, and then you find out if you were successful or if you have to redo it. So Polycam is quite enticing to use because you can also use LiDAR, as long as you have a smartphone that has that capability. So here on the left is just a video of where that 9 by 8 meter structure is at the top of the site. The middle is the 3D model of the space captured using LiDAR, which took about 15 minutes. And to the right is a zoomed in image of the cluster of rocks that extends from the structure. However, if you'll notice where these two arrows are pointing, you might be able to see some of the gaps within this model. This is because larger areas being captured, the more data there is to process, which coupled with a difficult texture like sand can make it challenging. So this method might be better suited for individual artifacts or smaller spaces. First, on the left is a video of a section of one of the slingstone piles. An image of this section is shown in the upper right. This scan was captured the texture of the sand a lot better because it's a smaller area and less data intensive. This next image is a capture of one of the incised pebbles in situ, which means in place. And this last video on the bottom right is of the ventifact in situ that we saw a few slides ago. So photogrammetry captures the cultural materials itself as an individual object, and LiDAR captures cultural material within its original context. Both are helpful in their own right, depending on what you need it for. So why did I do this? Thank you so much for asking. So the GoPro worked really well, but you have to wait until the end of the day to process the data, and the files are really large. The app also works well, and you can process it immediately in the field, but the quality can vary based on the texture and the size that you're trying to do. I needed to create 3D models to incorporate in my simulated environment. I wanted to see if game theory would work to highlight areas of interest. And I didn't touch on this, but it's really important to read the licensing agreements in terms of service of anything that you're using so that you understand who owns the models that you're creating and what they can do with it. And they often update these agreements, and they're very complicated in legalese. And I reached out to one of them recently, and they told me to consult a legal counsel. So they're not super interested in helping you, but it's also really cool. And with that, I just want to thank the Dan and Betty Churchill Exploration Fund and everyone else who has helped me along the way.
We have time for a question or two.
Oh my, Maddie. Yes, there is we believe they came from the Santa River, which is like 5 kilometers-ish away, and would also have served as the freshwater purpose for both sites for the inhabitants. So they're really just round cobbled stones that you can tell they're water worn. And they were all just, we believe, sourced from the same area and transported to this site.
Was the Santa River in a different position when the site was occupied?
It has been hypothesized by Dan. I don't remember what year it was, but
A long time ago.
yes.
I may have been, well, it wasn't, but not in a seriously different position. It would have been a few kilometers at most. It was still streaming stuff north. Yeah, and that's probably where they came from.
We'll talk after.
What seeing what you were doing there, it struck me that you were wandering around this site, leaving footprints and picking stuff up and scanning it. So after you've done all that, does that count now that the site is disturbed, or do you put everything back where you found it?
Any of the models that I create, I mark where I have taken them from, and then they go right back to where they are as best as we can replace them. They're all on the surface, so it's not like we're digging and excavating anything. This is all surface collection.
Yeah, and so how do you account for folks that might have done that in the past?
We know of everyone who's been at the site. It's been Dan who's excavated at the site, and then John Topic has been there, I think in the late 80s, to look at the slingstone piles, and he documented all of the piles that he had interactions with. And we did the same so that people in the future know what has been disturbed. Thank you.
Cool. Thank you so much. All right, next. All right. Our second talk is from Thomas Grindle, speaking on how do lakes in West Greenland recover from abrupt lake browning following compound climate extreme events.
Thank you very much. Hi, as was mentioned, I'm Thomas Grindle. I work with Dr. Jasmine Saros, and I am studying an abrupt and cohesive lake browning event that happened following a unusual for the area rainstorm in West Greenland in 2022. So, my area of study is Kangerlussuaq, West Greenland, and it is the site of what was formerly the largest airport in Greenland prior to the opening of Nuuk International a couple of years ago. It has a year-round population of about 500. It is continuously underlain by permafrost, or at least in the area that we study. As you get toward the coast, it kind of leaves out a little bit. And the landscape is considered subarctic and the climate considered arid, which is a little unusual for the Arctic, but for the coast of Greenland is perfectly normal. It is also pockmarked by lakes. There are 2 lakes in particular. You'll see later why I called those ones out. But the entire region has dozens, if not hundreds, of these small lakes. And these lakes are crucially pretty like closed basin. Some of them have an inflow, very few of them have an outflow. So keep that in mind as we consider what happened later. So in 2022, we had this compound extreme event, by which I mean there have been precipitation extremes and there have been heat extremes in this area before. They have occurred individually, and that's never really caused that much of an impact on the landscape on the scale that I'm talking about now, because they've never happened at the same time before. So if you had a precipitation extreme, you would have probably snow falling in late September, early October. That's typically when during the year it would happen. And if you had a heat extreme, you would just get a heat wave. When you get both, you get rain. And rain impacts the landscape in a much different way from snow or from an ice storm or from just a dry heat wave. And so what does it do? It does this. These pictures were in 2024, so about a year and a half after the event actually happened. Water tables on the lakes were still high. There was overland flow that, as if you can like look in there, it's actually flowing over grass still. So it's not an established channel. It is just that the hydrology of the lake previously was not prepared for this volume. And it also caused really kind of large channelization of the permafrost on the landscape itself. So the rain would have cut a channel through the permafrost and hastened its degradation, hastened its erosion. Those channels typically don't have overland flow still, but some of them do. So what does this cause? This caused very rapid, very large-scale browning in the lakes of the region. Previously blue lakes are now just, in the course of less than a year, brown. That happened, I believe this picture was 2022. That one was 2023. You might have heard of brownification of lakes in the Arctic. This isn't the same process. Brownification of lakes in the Arctic is a kind of broad scale push of more of what causes browning into a system. This was one pulse that just swept a landscape that is arid, not typically exposed to water all that much or that much precipitation, into the basins of the region. And so it's large scale, it is abrupt, and it's coherent across the landscape. All of the lake systems that we have studied in Greenland, and that we being the lab, that the lab has studied in Greenland for the better part of 15 years, were impacted by this. All of them turned brown. Browning is driven by iron and dissolved organic carbon, principally. Those are kind of the 2 factors that deal with it, and then there's some complexities in there. And my aim is to understand how that post-disturbance chemical environment informs the trajectory of browning following this event, because this is not well documented in the literature. This kind of pulse disturbance is unusual, highly unusual to our knowledge. So there are a number of possible ways that this could go in the future. These are only 4 of many, many ways that this could potentially proceed. This will come back up, so don't feel the need to read all of that, but we don't know how the browning will go. The browning could intensify, the browning could recede out of nowhere. We're not sure. It's really a point of contention. in my thought process about the region is how do we prepare for something that we have no idea how it will go? We've never seen it. So this is what's actually happening in the lakes. Pre-disturbance, you had a pretty deep penetration of light. That becomes important in the chemical environment because light penetration informs both ecosystem processes and physical processes of these lakes. That light penetration determines often the thermal structure. Previous studies of these lakes prior to the disturbance showed that light penetration was one of the primary factors impacting how those lakes stratified, the oxygen within the lakes. And so after the disturbance, when you have all of that iron and carbon, which is more or less what permafrost is, just pouring into those lakes, you get browning, the light penetration drops really quite astoundingly, and it impacts how thick the hypolimnion is in the bottom and how that kind of has interplay further down the chain. So what is dissolved organic carbon? One of our two puzzle pieces in browning. Dissolved organic carbon is kind of a mess of carbon and hydrogen and also whatever else got swept up in there. It's typically not that resembling what it used to be because this has been dissolved, it's been combined, and it's just kind of a mess. But it's broken down in a couple of ways. The really important one that I'm studying is photodegradation and photobleaching. They're kind of similar effects in that they're both just exposure to light, but photodegradation breaks it down into smaller pieces of carbon, while photobleaching targets those aromatic rings, which is what actually causes that DOC to be brown. DOC is not in and of itself like brown. You can have colorless DOC, and indeed we did. This is, believe it or not, there are supposed to be two columns here. The blue was the DOC as characterized by Dr. Rachel Fowler of SBE prior to the disturbance. You'll notice that there's not a whole lot of blue there. That's because after the disturbance, there is just a really significant change in how the DOC reacts to light exposure. So prior to the disturbance, it was very recalcitrant. It would have been very small chain, very colorless, non-aromatic. After the disturbance, when you expose it to light in a controlled environment, you get measurable breakdown of the carbon in two different lakes that we studied, SS2 and 901. Those are at different points on the landscape. They're not particularly close to, or SS2 is not particularly close to the Greenland ice sheet, while 901 is ice sheet adjacent. So across the landscape, the character of the DOC in the lakes has changed, and that's important with how it reacts to the browning. Remember that these lakes are in the Arctic. They're exposed to 24-hour sunlight for a good period of the year. So we would expect to see some form of photodegradation, some form of photobleaching. We didn't before the disturbance. After the disturbance, we do. That will change how it reacts and how browning is propagated. Oh, yes, I also had a slide telling this. Importantly, it also indicates change from an autochthonous, which is created within the lake source, to an allochthonous, which is created out of the lake source. So there is compelling evidence that the DOC itself that is causing the browning originated from outside of the lake, as opposed to you got an influx of nutrients, there was a big hit of productivity, and it made a bunch of organic carbon. We think that the carbon that's in there now, off the landscape. The other part of it is iron cycling. Iron cycling gets real complex real fast, but in the context of browning, what is important is oxygen in the water column. Iron 3 and iron 2. Iron 3 is typically in the form of iron 3 oxides. They're precipitate, they are often particulate, and they sediment out. Iron 2 is dissolved, it is colorless, but what it does is when you get an anoxic bottom water, that iron can redissolve into the water column, which can get cycled up. As soon as it hits oxygen, it becomes iron 3, it becomes brown again. So that the way that browning kind of continues through the water column is by that resuspension mechanism. And we measure that with with ferrozine, which is a chemical that traps iron 2. I won't get into all of the details of our sampling method, but it has been problematic in the past to characterize iron 2 versus iron 3 because iron 2 disappears when it comes into contact with oxygen. So in order to do that, we take samples immediately out of the lake and essentially fix that iron 2. And just to return in conclusion to my possible future slide, we don't know how this is going to proceed. This is a new system to the scientific literature in this context, and I'm very excited to find out, but we won't know until we go back. So going back in June, I'll keep you updated. Thank you very much.
Like that leave a signal in sediment core. Have you or anyone else moved back in time to see if this is happening?
So there is some difficulty in doing that because both iron and VOC have problematic histories with, like, in the sediment themselves. The resuspension of iron means that unless a lake has a really, really fast deposition rate, it's going to move through the water column and it's going to get brought back up and set back down. And the sedimentation rate in these lakes is very slow. Similarly, organic carbon is an excellent source of nutrients for all of the things that live in those bottom waters. And so dissolved organic carbon records in sediment cores is also a little rough. We did pull sediment cores though, and I didn't include the picture, but you can see iron flocculant just on top. It's just sitting there. You can see like the sedimentation visibly on the top of any sediment core that you take. So it does show up on the bottom of the lake, but has an actual impact in the sediment core might be difficult to really rigorously try to demonstrate. Yeah.
Following on Brenda's comment, except for the modern era, if you take a look at the precipitation records from the region, how unique is this particular event?
So for the precipitation records for the region that we have in the modern era, quite. I didn't include the standardized chart, but the precipitation was, I think, 4 standard deviations above normal. So for a precipitation event, it was significant. It was hit by an atmospheric river coming up the Atlantic is where all of that moisture came from. And then it was hit by 8 more in the same season. So it is a particular confluence of factors that we don't think has shown up in the region before. I believe so, yeah. I think that's as far back as we have records.
Comments after our speakers?
Thank you very much.
Great, thank you, Thomas. And our next speaker is Sarah Thomas, speaking on the geochronological record of ice extent during the Antarctic cold reversal at Bahia Penhot, Chile.
Good morning, everyone. Thanks for being here. I'm Sarah Thomas, and today I'm going to be sharing with you some of my thesis research concerning ice behavior in the Cordillera-Darwin ice field in Chile at the end of the last ice age termination. So the last ice age termination was the largest climate change of the last 100,000 years, but we still don't really understand how or why it occurred. And understanding the driving mechanisms for the last termination can help us deduce how Earth enters and exits an ice age. So my research uses glaciers to track behavior of the Cordillera-Darwin ice field during the last termination to try to gain insight into its cause. In particular, I focus on the timing of the Antarctic cold reversal, or ACR, which was a cold period that interrupted the last termination warming from about 14.6 to 12.7 thousand years ago. And the cause of this climate reversal is unknown. At present, the leading hypothesis for the ACR is a bipolar seesaw, which calls for an interhemispheric redistribution of heat through ocean circulation. There are a few hypotheses as to why this occurs, one being a resumption of overturning circulation in the North Atlantic, and 2 being a possible meltwater pulse from Antarctica, both of which would cause cooling in the Southern Hemisphere. In both of these circumstances, the bipolar seesaw mechanism does require that climate conditions be out of phase between the hemispheres. So if this is the case, then in Cordillera-Darwin during the ACR, I should expect it to be cold in the Southern Hemisphere, therefore warm in the Northern Hemisphere. There's new evidence that is against this, though. Glacial records from both Norway, Scotland, and possibly even Maine suggest that there was a similar climate reversal with a timing similar to the ACR. So if these data are correct, then it would imply that there's some sort of global driving mechanism, such as the Zealandia switch, which I'll circle back to. My specific field site is at the southernmost tip of South America, located in Tierra del Fuego at about 55 degrees south latitude. On the image on the right, you can see the present day extent of the Cordillera-Darwin ice field, which it's the mountain range, the white in the middle. To the north, you might be familiar with the Strait of Magellan. To the south, the Beagle Channel. And down at the very bottom, the island is Cape Horn. My specific field site, Bahia Pinhot, is located at the center of the former ice field and is a branched fjord on the southern arm of the Beagle Channel. We found a series of well-preserved moraines at this location, which we thought to be late glacial. So my approach is to reconstruct an ice record in this region during the time, and through geomorphological mapping and beryllium 10 exposure age dating, which I then compare to other records in both hemispheres to see whether the ACR favors a globally synchronous or asynchronous event. This process started in the field. So we were in Cordillera-Darwin for about a month, about 4 days at my specific field site, and we conducted field work from a sailboat, which is shown in the top right. We collected drone imagery. I've included 2 drone photos on the top. On the left side image, you can see some nice boulder moraines on the landscape at Pinhot, and then also some field photos. One is Marina Miles collecting a sample for exposure age dating, and then one of our field crew members actually collecting drone imagery. So using the drone imagery that we collected in the field, I was able to create a digital elevation model, which I then used to map glacial landforms on the landscape at Pinhot. And I've divided this map into 3 different sections. The outer drift, which is represented by the orange color, western branch drift, which is that pink color, and then an area of scoured bedrock. So the outer drift is characterized by streamlined bedrock features, which is overlain by a very thin drift deposit. And there are scattered erratic boulders over here. At least within my field area, we didn't observe any moraines out here, which is different to the western branch drift, which is located on the peninsula where the 2 branches of the fjord meet and extends along the western branch. This is an area of bedrock which is overlain by a thicker drift deposit and does have several low-lying moraines, about 11 that we counted. And these are oriented perpendicular to the streamlined bedrock features. Inboard of that, there's an area of scoured bedrock with abundant erratic boulders. Right now, I have 30 dates, 30 boulders dated from this region spanning between about 12.3 and 14.2 thousand years. So we will look at each of these units individually. So right now I have 2 boulders dated from the outer drift, and they form a mean age of about 14,000 years, which is slightly older than the rest, but again, with an error to my other dates. Inboard of that, the western branch drift is where most of my samples come from. Altogether, they form a mean age of about 13.3 thousand years. And due to time constraints, I'm unable to show you ages of specific moraines, individual moraines, but it should be noted that the outer moraines and inner moraines are virtually the same age, which indicates just a fluctuation of the ice margin at that position for several hundred years before retreating. And then finally, inboard of that, the scoured bedrock, I've dated 6 boulders here, which come to a mean age of about 13.5 thousand years. Again, very similar ages to the previous 2 drift units. If we look at all of the samples I've dated at Pinhot, they form a nice cluster at about 13.3 thousand years. And this age probability plot really just emphasizes the fact that all of these boulders were deposited around the same time, which is consistent with the timing of the ACR. So if you recall, the first step towards testing different mechanisms for the ACR is to determine if it was a globally synchronous or asynchronous event. So here I've plotted some age probability plots from my field site in Cordillera Darwin against some of Aaron Putnam's work in Western Norway and the Southern Alps. So again, I date the culmination of the ACR at Bahia Pinhot to about 13.3 thousand years. And if we look to the Southern Alps of New Zealand, there's evidence of marine construction there at 13 and 12.9 thousand years, which is very consistent with the ACR, virtually identical to Cordillera Darwin. And then looking to the Northern Hemisphere in Western Norway, we see marine construction there at 12.7 and 12.8 thousand years. So these data support the idea that the ACR was a globally synchronous event between the hemispheres. And if that's the case, then the bipolar seesaw mechanism is insufficient to explain why this event was globally synchronous. So instead, we have to look for some other sort of global driver, such as the Zealandia switch. So in review, I date the culmination of the ACR to about 13.3 thousand years at Bahia Pinhot, which is coeval with marine construction in the Northern and Southern Hemisphere in New Zealand and Norway. And if this is the case, the bipolar seesaw is an insufficient mechanism to explain globally synchronous climate reversals during the ACR. Thus, we have to look for some sort of global driving mechanism, such as the Zealandia switch, which calls for a latitudinal movement of the Southern Hemisphere westerlies, which has an effect on atmospheric greenhouse gases and heat storage and release from the ocean. With that, I thank you. If you're interested in hearing more, my thesis defense is next Thursday at noon. So thank you.
Thank you, Sarah. We have time for a few questions.
So can you go back to the last slide? We had all the ages of different.
Yeah.
So if you take your one and stick it on the bottom, it looks like I know there's a margin of error in the dates, but it looks like it's starting in the north and moving south.
Yep.
Or
So
not starting south, moving, it's getting younger, right?
yeah. So funny you should ask. I did figure out recently that I have to recalculate some of my dates based on an outlier that we recently threw out. So it should, once I do that, it should shift a little bit to be more similar with the other dating, but yeah. Any other questions? Yeah.
You mentioned possible evidence in where is that?
Say that one more time, sorry.
You mentioned possible evidence in Maine. Where is that?
Yeah, around Katahdin, I believe there's evidence of ACR, which there are other main experts in the room. But yeah. Awesome. Thank you.
Thanks so much, Sarah. Our next presenter is Kelly Hoover, presenting on using geophysical survey to reveal patterns in monumental construction at Los Morteros, Peru.
All right. Good morning. So I have conducted my research at Los Morteros, which is a late pre-ceramic monumental archaeological site located in the Lower Chow Valley on the northwest coast of Peru. It is situated on a paleo shoreline, visible in blue in image B, and wind direction blows sand from that southwest direction, generally perpendicular to the coastline. So here's a DEM made from an, at the time, UMaine graduate student, Kurt Rademacher, who's working with Dan Sandweiss and his team. This image shows 6 GPR lines that were run by Alice Kelly in 2006, revealing signatures indicative of walls and floors in the mound, thus shifting the classification of this site as an entirely natural dune formation with later occupation to something that could be a built feature. This survey marks the beginning of the work done at Los Marteros to define human construction and occupation, which is what I am doing now. The mound is measured at 15 meters in height and is 200 meters by 225 meters in length and width. To the right is this image at Los Marteros where you can see a really small Alice Kelly and myself, just for size comparison. So in 2024, our team collected nearly 20 kilometers of 600 megahertz and 170 megahertz GPR data, ground penetrating radar, over the mound using a dual frequency radar with single wheel attachment pulled by rope tied to each handle. You can see that rope in the bottom image. Lines are spaced out 1 to 2 meters, and XYZ coordinates of the survey are recorded by that internal GPS system. The data was then processed using Geolytics, a cloud-based processing software for GPR. Just for this research, only the 600 megahertz data, which prioritizes clarity at shallower depths, has been analyzed and interpreted. In Geolytics, I have performed various filters and processes to best reveal patterns and information. These processes are listed here at the bottom of the slide. So I have made this map showing the locations of the 2012 excavations completed by Dr. Cecilia Mauricio for her PhD dissertation on Los Marteros here at the University of Maine. This was published in 2015. The archaeological reports detailing these excavations are currently being used to confirm stratigraphy within the radar data, but as you can tell, only one excavation, Trench 2, that purple one right in the center, was extensively overlapped by GPR survey. The GPR data collected in the 2024 season has been analyzed using a facies model. GPR detects contrast and dielectric properties, so moisture content, material composition, or density within the subsurface. And these contrasts can then be grouped into radar facies, a unit of subsurface defined by its unique reflection characteristics. With that, a facies can reflect patterns of material, geological processes, and other similar things. This approach was chosen because it allows for the identification of repeating patterns throughout uncertainty. So while I would always be able to identify exactly what these patterns represent without extensive ground truthing, we can use reflection patterns as proxies for specific repetitive patterns in the data. This way, a certain amount of ambiguity will not take from the importance from findings. Additionally, by organizing radar reflections vertically into facies, you are building a stratigraphic chronology that can help interpret construction sequences, similar to what is done in archaeological excavation. And most importantly, this type of facies interpretation allows for various spatial analyses to be conducted. This includes depth grids of facies boundaries, thickness maps of anthropogenic and geological zones, and the possibility for meaningful 3D reconstructions based on facies boundaries. So here I've identified 4 major facies that occur repetitively across the 2024 GPR data. In the table from left to right, you can see the radar facies numbered, with the lowest RF1 representing patterns occurring at the most shallow depth, and the highest number RF4 occurring throughout the entire analyzed area, but to those deepest depths. I've included an image directly from Geolytics as an example, and then sort of a crude drawing right next to it just to show you exactly what I'm looking for. These facies are named for their general appearance and then described in greater detail in that description portion of the table, but I will go into even more information coming up. So the shallowest occurring radar facies, RF1, represents a horizontal continuous return with high coherence. These are either flat or gently dipping, and it is likely that this is alien homogeneous sediment, like sand, blown onto the surface of the mound from that southwest direction. The maximum depth of the layer is about 2.2 meters and is found in the southernmost portion of Los Marteros. Though, I will say, excavation reports by Cecilia Mauricio show sterile alien sand persisting to about 4 meters. In one of her excavations, Trench 1. This is on the southernmost ridge of the mound, and it is outside the scope of our GPR survey. The next radar facies, RF2, represents a generally concave down reflection with medium to strong amplitude. The material represented by this facies is most likely homogeneous and structured. So these characteristics lead me to interpret it as having an anthropogenic origin, potentially sand building up on top of existing structures. RF3, right here, represents a diffuse amplitude reflection and is characterized by an almost fuzzy appearance in comparison to those clear surrounding reflectors. The material is likely a cluster of condensed low resolution material like small rock, shell, clay-rich materials. And when it is contextualized with Mauricio's excavation reports, this facies occurs at a depth that is repeatedly characterized as a compacted anthropogenic material and interpreted by her as an occupational layer. This facies has a higher occurrence on that upper southern end of the mound, with little to no occurrences in the northernmost portion of the site, as you can see in this map. The most broad facies is the fourth. It is characterized by subhorizontal chaotic return and described as semi-continuous to discontinuous, and it contains various amplitudes. It exists from the surface in some cases and all throughout the line to those deepest depths analyzed. The material is heterogeneous and consistent with the excavation reports as aeolian sand mixed with charcoal, fishbone, shell, and rock. Here is line 77 of the GPR survey, which overlaps with trench 2 of the 2012 excavations. The 2 by 2.5 meter column right here in this line is that trench. And I have made it mostly opaque because that internal material is representative backfill, is not meaningful to me. But that surrounding area is undisturbed by excavation and is the focus of those stratigraphic comparisons. Below the image of the line is a table describing the stratigraphy defined at this location from those reports detailing her findings and interpretation. Thank you. Now, that red dot was actually an excavated stone-lined hearth, and that the charcoal surrounding this hearth was dated to the earliest securely dated and calibrated cultural layer, which is 5,726 to 5,477 calibrated years before present. So it's really cool to see that on the GPR data. But all of this is ongoing. This research uses non-invasive methods to preserve site integrity at Los Marteros, and our findings do suggest a generalized floor plan for that terminal occupation of the site, which is currently considered to be constructed during the late pre-ceramic period, 5,800 to 3,600 years BP. Further interpretations and findings will be available in those coming months. In the coming months, with me completing my thesis in August, and then I will be presenting this work next week at SAA. And I am also submitting for a manuscript in Heritage, an open access MDPI journal. So with that, I'd like to express my deepest gratitude to Dan and Betty Churchill for funding this research via the Dan and Betty Churchill Exploration Fund and everyone else listed on this slide. Thank you. Go ahead.
If the goal is to sort of link non-invasive techniques with, what's known from excavations, why so little overlap between your survey and then sites in that?
So the excavation was completed before this survey was conducted without the intention of linking the two. Yes. And then the hope is that with this survey, future excavations at Los Marteros can be targeted to individual areas and really prioritize those more meaningful areas and hopefully reduce destruction elsewhere by excavation. Thank you.
Can I just add to that?
Yeah.
So Cecilia did a lot of work at the site over a number of years. and was
15.
looking specifically for some of these big structures, and she just missed a bunch of them by like 40 or 50 centimeters, right? So having these data is going to make the invasive part of the future research much more targeted, destroying less, but getting better results.
Exactly. Yeah. Go for it.
Your spatial map of the first species, it showed that the windblown sand was like less than 50 centimeters in some areas.
In some areas,
Yeah. And so my question is,
yes.
what's below that? Is there other species that you've defined here? Or do you eventually hit like solid rock, or what's down?
Right now, I'm only interpreting to about 2 meters, which is really not that deep. But the majority of that is that subhorizontal chaotic return, which is the mixed alien sand with cultural materials, so like the charcoal, the shell. Below that, I'm hoping to get the time to analyze that 170 megahertz data, which will allow me to get deeper and deeper with my analysis. It'll just kind of sacrifice a little bit of that clarity and refinement. But yeah, I expect to see more cultural layers and then that to turn entirely geological. Yeah.
Thank you so much.
Thank you.
Continuing on, our next speaker is Megan Spa, speaking on the Cordillera-Darwin ice field extent during the last termination.
Thank you. Thank you all for coming. As just stated, we're going to go back down south, looking at the Cordillera-Darwin ice field once again during the termination of the last ice age. My research focuses on two really big questions. First of all, what caused the termination of the last ice age? This is a huge question, as the termination is one of the largest climate events during the last 20,000 years, and we aren't sure about the mechanism behind it. In order to answer this question, we have to understand when, where, and how fast the termination was. And with these answers, we can possibly start to look at the mechanisms behind the termination. So taking a look at southern South America, the extent for the South American ice extent is thought to have been much larger during the last glacial maximum. It then collapsed down to the northern Patagonia ice sheet, the southern Patagonia ice sheet, and the Cordillera-Darwin ice field down at the very south within the red box for my field site. Studying in this region is very important for understanding the mechanisms behind the termination, as this position is the most southern landmass for the southern hemisphere westerlies as it circles around the globe. This site is also close to the Southern Ocean. Both of these have been proposed to be drivers for the termination of the last ice age. So today, the westerly winds are displaced south, which is bringing warm subtropical air to the latitude of the field site today. Also, as the westerlies are displaced south, they are increasing the upwelling potential of the Southern Ocean, and this pumps carbon dioxide from the deep ocean up into the atmosphere. Both of these could cause warming. As I'm studying changes in ice extent, this is a proxy for summer temperatures. So by having these two potential drivers for abrupt warming, I can test it through changes of ice extent. Taking a closer look at Cordillera-Darwin itself, it's that little tiny mountain range that is host to an ice field today. The red line is from Caldinius in 1932, and it's the last glacial maximum moraine belt surrounding this region. Ice is thought to have last occupied this moraine belt at 18,500 years ago. Ice would have radiated out from the ice field that we have today at Cordillera-Darwin to that red line, and then during the termination, collapsed back to the ice field we have today. My field site, very similar to Sarah's, is within the southern range of the Cordillera-Darwin mountain range, which is host to the Cordillera-Darwin ice field. My field site is that Pia Fjord, that beautiful Y-shaped fjord at the top within the mountain range. And specifically, I'm focused on a valley called East of Pia, EOP. We're going to see that on the next slide. Once again, this is the ocean tramp. For the field seasons of 2023 and 2024, UMaine hosted an expedition down to the site. I was part of the crew. We lived on this boat for about 4 weeks each year. From that boat, it was our home base to take a zodiac and map the region for glacial geomorphic features and to sample for things that could date ice extent through time. So with this, we were able to travel along the Beagle Channel to all of these points of interest. So back to my point of interest, this is east of Pia. On your left is the Pia Fjord itself, and on the bottom we have the Beagle Channel. I could just describe it from here. So my valley, ice would have been coming from the top of the photo of the Cordillera-Darwin ice field and feeding into the Beagle Channel itself. The moraine now preserves the moraines, showing the ice retreat through time. Also part of this valley is preserved erratics that would have been deposited when the ice lobe itself was within the Beagle Channel. We're going to have a better photo soon. As I mentioned before, the boat itself was our home base, so we would eat breakfast on the boat and take the Zodiac to shore. From there, the landscape here is extremely boggy, so we would take our rain boots and hike all throughout this region. We would be mapping features, primarily moraines, which is showing past positions of the ice, and also mapping erratics, which are boulders that were deposited by the ice during its retreat. So when we found a perfect sample, which would be a beautiful large erratic embedded on the crest of a moraine, we would start documenting the boulder itself. So that would be measuring the boulder, measuring exactly its position and elevation, taking shielding for our cosmogenic exposure dates. And then finally, at this very bottom picture, we are taking a subsurface of the sample of the boulder. This sample was then sent back to the University of Maine. And at our in-house cosmogenic isotope lab, I would extract the beryllium from the quartz-rich content of the boulder. And through a lot of mathematics and statistics, we have an exposure age for how long that boulder was there, which we infer to be a position of the ice in time. With all that, plotted here are the exposure ages for each of the boulders we collected in the 2023 and 2024 field season. Taking a look at our results, as I mentioned in the introduction, the ice was at its maximum extent at 18,500 years ago. And here at the heart of the Cordillera-Darwin ice field, we have that the outboard erratics are suggesting that the ice retreated to this position by 18,000 years ago. So this is showing that there is a very fast and very large collapse of the ice sheet at the beginning of determination. So ice would have collapsed down to its near Holocene position in a matter of centuries. So bringing that point home, the outermost moraine here at east of Pia is dated to 17.8 thousand years ago. And that means the ice reorganized from its 18.5 thousand year position to 17.8. So once again, this is just highlighting how fast the ice collapsed in on itself. Moving up valley, there are a series of moraines in this east of Pia site. I'm not going to jump into it too much for time, but this is suggesting that there is a millennial scale pattern to the termination retreat of this ice lobe for Cordillera-Darwin's ice field. And just a call back to Sarah's presentation, here at east of Pia, there is also a readvance at 13.4 thousand years ago, which is thought to be the Antarctic cold reversal signal at this site. So once again, this is a very regional signal. With that, I just want to re-highlight my conclusions. So at 18,000 years ago, the retreat is big and fast for the Cordillera-Darwin ice field. Most of this ice field disappears shortly after 18.5. We are seeing that there is a millennial scale pattern to this retreat that I'm going to look into in the future. Once again, we have that ACR readvance happening at this site. As I suggested in my introduction, looking at the magnitude and speed of this area, we can see that there is extremely rapid warming happening for this site. So based on the proposals for the termination of the last ice age. This site suggests that the westerly winds may have been displaced south very quickly at about 18.5 thousand years ago. That would have brought the rapid warming to this region. That would have brought that warm subtropical air to this glacier, causing this very rapid collapse of the ice field. So the next steps will be looking at all of the sites that we collected during these two field seasons and comparing them to one another. And then also future work will look at constraining that last glacial maximum timing to determine if the ice was truly last occupied there at 18.5 thousand years ago. And I want to give a big thank you to the Churchill Exploration Fund and NSF that made all of this possible. I want to thank the Ocean Tramps crew and captain for getting us all home safe, and all the members of the 2023 and 2024 field seasons for making this extremely productive.
Where did you start from, in the ocean trend?
Yeah,
Where
we
did you begin?
so we flew to Punta Arenas and then took another small flight to Puerto Williams, and that was our point of call for getting onto the boat itself. Yeah, it's beautiful down there.
What was the weather like?
Extremely variable. It rained a lot. We had a few snowy days, but then there would be some like beautiful sunshine days, and it was just lovely, and everything would dry out. Yep, all weather. Yeah.
So much, Megan. Our next presenter is Katie Westbrook, and Katie will be speaking on interhemispheric comparison of the late glacial climate reversal.
Hello, everyone. Today I'm going to be sharing work that I've been doing trying to pin the timing of a climate reversal in Lysefjord, Norway. Later on, I'll be sharing data that suggest that moraines such as this one were constructed in Norway at the same time as the Southern Hemisphere. And this is a clue for our understanding of what drives millennial scale climate change during the last glacial maximum termination. So I'm going to take us on a little trip from the United States all the way over to southwestern Norway to a fjord called Lysefjord. From, let's see if I can find the mouse here. Oh, it's so small. From the mouth of the fjord to the head. Okay, well, you can see it. It's about 30 miles long. The fjord walls are about 3,000 feet high, and the deepest parts of the fjord are 1,000 feet deep. So during the later part of the termination, this fjord would have hosted a large volume of ice. It's, in addition to the incredible glacial geology here, it's also historically significant. In 1824, this was the site of the very first theory of ice ages, published by Jans Esmark. We're looking at the valley adjacent to Lysefjord, and in the center of the image, perpendicular to the valley, you can see the Esmark moraine, named after him. Much later, in the mid-1900s, a fellow named Bjorn Andersen also mapped the area. He was a colleague of George Denton and Hal Borns, and he laid a fantastic groundwork for the work that we're still doing today. During the LGM, the ice from the Scandinavian ice sheet extended well beyond the modern coastline of Norway. Today, ice only exists in isolated valleys, and along the coast, you can see a prominent set of moraines that extend all the way across Norway and Scandinavia. The presence of these moraines indicate that there was a climate reversal. So cold conditions that would have been suitable for moraines to form during the termination of the last glacial maximum. In this box here is Lisa Fjord. So let's zoom in. Here's a LiDAR image of Lisa Fjord mouth. You can see, maybe the mouse will work. Along the right lateral side, or the upper portion, you can see a belt of several moraines that cross over Lisa Fjord mouth to the left lateral side, up and over the bedrock plateau, which is where Trisha's dates were, if you had attended her presentation yesterday. Those same moraines continue around to connect with the S-mark moraine. On either side of the moraines, there's also scoured bedrock that host numerous erratic boulders. And these features in Lisa Fjord mouth are where I'll be focusing on today. They're undisturbed and beautiful. Here's a photo of what those moraines look like in a portion. You can see 3 distinct moraines scattered with lots of boulders. So to build a chronology of the Lisa Fjord mouth area, I'll be using beryllium-10 surface exposure age dating. And more important to our understanding of the ages is the geologic context of where we get those boulders. Dating a boulder from the peak of a moraine tells us the last time that the ice would have been there and stable enough to produce a moraine. I've also targeted erratic boulders. This tells us where the ice front position was when the ice was unstable. We also came across several rock moraines, which are just really neat for glacial geologists. There's a famous rock moraine in Norway called the Trollgarn moraine, which translates to troll fence in English. And before a geologic explanation, people believed that these moraines were, or that these features were created by trolls. And can you blame them? So in August of 2023, me and Trisha Collins collected about 50 samples from the Lisa Fjord mouth area. We take just a little piece of rock from the top of a glacially deposited boulder. We bring it back and crush it, isolate the quartz, isolate the beryllium, and apply a production rate to figure out how long those boulders were exposed after they were dropped by the ice. So here is the LiDAR image again, only this time I have plotted in orange dots the sample locations of all of the boulders that I have ages for so far. You can see outside of the moraine belt, I have several boulders. I have several samples from erratic boulders. I also have samples from the moraine ridges themselves, and then several more samples from erratics inside of the moraines. And so here are all of the numbers so far. And this is probably too much to digest just all at once. I wish I had time to talk about every single one, but I don't. So instead, I'm going to rely on statistics. I have calculated the averages for each individual feature to get an idea of what the ice was doing as it deposited these features. So if we start outside at the erratic boulders, this age is going to tell us when ice was retreating and the initial pulse of the termination. And so I have ages that suggest this ice was retreating at 15,300 years ago, based on 5 samples. The ice then paused to produce several moraines between 13,500 years ago and 12,800 years ago. The upper moraine you can see there is a composite moraine, meaning it has 2 age populations split between the 13,500 and the 12,800 years ago. And then just inside, we have our erratic boulders that are statistically indistinguishable from the innermost moraine, which suggests that is exactly when the ice started retreating from the mouth of Lisa Fjord. I'm going to turn our attention to a field site in New Zealand. This is work from a previous UMaine student, Peter Strand, on the Lady Emily moraines in New Zealand. So this is a tributary valley of the Cass Valley. Ice would have been filling in this area and connecting with the larger valley outside. And I'd like to turn your attention to two of his moraines in particular in the foreground for comparison. This is a camel plot. So it's a statistical way to look at the ages of all of the moraines or all of the samples. So on the top, I have plotted the New Zealand samples. Each individual little curve is a single sample, including its uncertainty, and the larger curves is the cumulative total of all of those ages. And you can see two moraines plotted. The innermost for the New Zealand samples were constructed at 12,900 years ago, and the innermost, or excuse me, the other way around, the innermost was 12,900, and the outermost was 13,600 years ago. And for Lysefjord, Norway, they are statistically indistinguishable from the New Zealand samples. And so when we're considering a theory for millennial scale climate change and for drivers of that, we need to consider the fact that Norway was operating synchronously as the Southern Hemisphere. And I would also impromptu like to highlight that the ages are nearly identical to Sarah's ages that we just saw. With that, I would love to take your questions. Yes,
So we can go back to the other block, and slide back.
sure.
See the New Zealand 12,970 date, n equals 3, is that enough to give you a good confidence, or
So
get a few more?
sure. Well, I personally will not be getting a few more. For this data set, all three of the samples create a normal distribution on the plot, so without any outliers. So I would argue that that is enough. That's statistically significant. More field locations could supplement that. Sure, 3 is less than 24, certainly.
Thanks so much, Katie.
Thank you.
Next, we'll hear from Xander Roman on the Little Ice Age glacial advances found in the Southern Alps of New Zealand at 43 degrees south, suggesting a global event.
Thank you for that mouthful. That is my title. Hello, I am Alexander Roman. I am a current PhD student with Aaron Putnam, and I'm here to give an update on the work that I've been doing past 2 field seasons. Where yes, I have indeed found little ice age glacial advances in the Southern Alps of New Zealand at 43 degrees south. So to give an overview of the work of this particular project of mine, it's to obtain evidence to determine if the little ice age and perhaps even the medieval warm period, if these were global events or not. And by doing so, I can then begin to address certain questions, such as what was the long-term global signature of the Holocene? Was the entire planet warmer? And if so, what can this say about certain climate dynamics? What were these Holocene moraines phasing with elsewhere? Is it related to solar variations, insolation, internal ocean atmospheric dynamics, force stochastic variability with volcanoes, some combination of all of them? I don't know. That's why I went there. Okay, so let's take a step back. Let's take a breather. What even was the Little Ice Age? Well, it was first a term coined and introduced into literature by Mathis in 1939 to describe an epoch of renewed but moderate glaciation that followed the warmest part of the Holocene. Now, you can take his word for it. I wouldn't. I like to look at data. Yeah, so we have a lot of data, mostly from the Northern Hemisphere of its existence. That's also primarily due to its notable effect on European agriculture during the late 13th and early 14th century. Now, each of these are just multi-proxy temperature reconstructions from several areas around the northern hemisphere. I can't spend too much time on this, and I don't want to because it's not my data. But quickly, just the red box highlights the generally agreed time periods for the medieval warm periods, and the blue box is the little ice age. And just taking a quick glance at this, there's a lot of agreement between all these different sites from Greenland, Scandinavia to Siberia to generally just North America. Now, fun stuff, because it involves me. So I have 2 field areas in New Zealand that I went to between 2023 and 2024. Well, Elsa Stream, right off the Cass Valley, is denoted by that red dot there, and then a bit more northeast up the Southern Alps. I also visited South Ashburn. We're going to start with Elsa Stream, that's it. Right off to the bottom right is actually the Cass, and this is a tributary valley. I just have 2 areas here that I collected samples from, an upper and lower section, and we're going to start with the upper section that had 2 distinct cirques, a western and eastern cirque. Now, what caught our attention about this particular field area is this stark difference. This is not doing it justice. This is pink, trust me. There's a stark difference in these 2 moraines. The innermost moraine is constructed, contains mostly boulders that have this muted gray color. And then directly outboard of it is another moraine, but these boulders are actually much more pink and reddish. And now what that tells us is that these boulders are 2 distinct weathering schemes. This innermost is very young. These boulders have barely seen anything. They don't even have to pay taxes yet. Well, these ones out here, they've been exposed to the elements a lot longer. This orange pink color you're actually seeing is from the iron inherent in the matrix of the boulder. It's beginning to oxidize. So that's what immediately caught our eyes, that these 2 moraines were constructed from vastly different time periods and represent 2 different glacial advances. We also collected a few boulders, that glacial erratics on glacially molded bedrock in the eastern cirque. So this is a preliminary geomorphological map made of that area. All this pink, all this yellow is just what I defined as span or scree. But what's really important is this purple color, which are moraines and moraine ridges that from the latest Holocene, and then just outward of that, this pinkish color are moraine and moraine ridges from early to mid Holocene. And each one of these little dots represents a sample location, chunk, focusing mostly on that pink and gray break in the western cirque, as well as a few of those boulders on that glacially molded bedrock, and even some of the boulders from the moraines in the eastern cirque as well. Now, moving a bit lower to the valley and that other red box, I have also collected several samples from here, and there's actually a distinct difference in the geomorphology of these 2 areas. The moraines here, as you can probably tell, are much more vegetated. They have a lot more soil cover. There's actually, there's still prominent belts here, but the boulders there have a much different weathering scheme. From further up the valley, they're still very angular. There's not much relief in the quartz veins. There's little to no lichen on them. Well, these ones down here have a nice hefty scruffy beard of lichen. There's multiple millimeters of relief for these quartz veins. They're much more rounded. So even if I didn't take ages from them, spoiler alert, I did, you can immediately tell that these boulders down here represent a much earlier time. So another map using that same symbology. These dark red colors represent the ridges, the pink is just general moraines. All the yellow dots are sample locations. Now between 2017 and 2023, over 20 samples have been collected from here. In this lower area, actually features 3 prominent moraine belts that actually seem to have been split and divided by an apparent slump. So when we were sampling here, we made sure to stay away from this slumped area, focusing mostly on these well-defined ridges. But we also got a few erratics that were deposited outboard of this off of toe mantle bedrock. All right, now we're going to head northeast of the Southern Alps to my other field area, South Ashburton, where I collected samples in 2 field seasons, and that little red box there, for a very similar reason, had that same pink gray break that we're seeing at Upper Elsa. So there was snow cover when we first went there in 2023. So when we selected samples, made sure to select samples that was well above that snow cover. Another map, say symbology. I'm hoping you're following along because I don't want to say it again. Each one of these yellow dots is just another sample. And we focus mostly on that large inner gray moraine, and then that moraine, pink moraine just outward of it, and then moving ourselves outward to the more pink moraines as well. And about 20 samples were collected here between those two field seasons of 2023 and 2024. Now I actually have a few samples from lower South Ashburton that Aaron Putnam, with the help of George Denton's student, Catherine Ledig, collected in 2010, that I've been able to actually adapt to my personal project. Over 20 samples were collected from these right laterals here, around the South Ashburton Glacier, and even around the terminus of the glacier itself. So how did we do it? Real quickly, we find a fairly flat area to set up a tent. Sometimes the wind didn't like it and it would eat our tent, but don't worry, we would get another helicopter to drop us off to a better tent. When that happened, I had to get real snuggly with a fellow college student, and that was fun. We would then trace the crest of the moraines, targeting large boulders that showed little to no post-depositional movement. Take a piece of it back with us to UMaine. Now the fun stuff, the ages. So this is from that lower Elsa section. I want to bring your attention to right here. So the boulders on that Tillman bedrock, around 15 to 16,000 years, which aligns with the timing of the Pioneer Stadium 1. Well, these three belts have ages that range from the late 12 to late 13,000 years ago, which aligns with the classic timing of the ACR. And as you can tell from Katie's previous talk, it also aligns with ages found in Norway. Coincidence? Probably not. Moving forward up the valley, I have ages from that western cirque. These outer moraines were dated to around 10,000, 11,000 years. Early Holocene. Make it real clear, and just I put everything else into just calendar years. The outer pink moraine was around 400 to 900 CE. It aligns with the almost the start of the medieval warm period, and then moving inboard, it actually aligns with the entire span of what would have been the Little Ice Age. And a very similar thing is found at South Ashburton, late 19th century for these inner ones, late 18th century for those outer moraines. I'm running out of time, so just as a conclusion, for all these ages that I found in New Zealand, they have spanned both periods of these centennial scale climate events. I have two ages that would span both the beginning and end of the medieval warm period, and ages throughout the entirety of the Little Ice Age. So that would suggest that maybe either the medieval warm period wasn't global, or maybe it wasn't warm at all, and the Little Ice Age may have had a global extent. Thank you.
I see that from the scalar that plot is northern hemisphere temperature anomalies.
Yes. The only reason for that is that there is a severe lack of any kind of plot revolving around. So this is a tree ring reconstruction.
Okay.
There's not nearly enough data to find and construct something to this of a high enough resolution for the southern hemisphere. So this is the best way I could get to trying to make that point across. And I think it drives my point further that a lot more work and a lot more data has to be collected from the southern hemisphere to truly drive this point home.
Thank you.
Great, thanks so much, Xander.
Thank you.
Our next speaker this morning is Tahi Wiggins, speaking on the surface water dynamics of the glacier. We get on. Thanks, Kaylee. So I'm excited to zoom forward in time. So instead of talking about ice in the past, we're going to move forward and talk about ice in the present. And I'm really excited to talk to you about Echo Glacier, but before I talk about this glacier specifically, we need to talk about temperate glaciers in general. These are glaciers that are at or near the melting point for much of the season, which is important for several reasons. This means that small changes in temperature can have big effects, and thus temperate glaciers are more sensitive to climate change. This means that they are also the glaciers contributing to sea level rise, as well as creating glacial hazards like outburst floods for those that live around them. Temperate glaciers are also interesting because their profile means that liquid water and solid ice can coexist in the same environment. This is important for ice dynamics. For instance, liquid water at the base of the glacier can lubricate the ice bed interface and cause the ice to slide faster. And liquid water within the ice column has an effect on ice rheology, which influences flow speeds. So it's really important for us to understand how liquid water is playing a role in temperate glaciers because this helps us constrain how temperate glaciers are responding to climate change. However, liquid water underneath or within the ice, as Renee explained, is pretty difficult to study. And so crucially, in temperate environments, most of the water that we find within or underneath the glacier is derived from the surface. And this means that if we can better constrain the dynamics of water at the surface, we can understand more about glacier hydrology overall. And that's where our study comes in. We're hoping to characterize glacier surface water dynamics at a glacier in Alaska in order to better understand glacier hydrology. And I just want to emphasize the importance of the surface. In Alaska, surface mass balance plays the biggest role in glacier retreat. And additionally, glaciers in Alaska are contributing disproportionately to sea level rise, as Renee also mentioned. This is the glacier where we're asking these questions, Echo. As you can see from this picture, it's an excellent place to study surface water. You can see a superglacial lake here, as well as a stream and some surface water stored in the snowpack. We can look at this like a satellite image too. That lake that you saw in the picture is the biggest one at the bottom of the figure, and ice is flowing up the screen. And Echo is located on the traditional unceded land of the Taku River Tlingit First Nation, which was in the title of my presentation. So as I said, our goal was to characterize glacier surface water dynamics, and we're doing this on a variety of timescales. So over the course of the presentation, I'm going to start with the scale of years and go all the way down to the scale of minutes. This is our glacier diagram, and over the course of the presentation, I'm going to be progressively instrumenting it, so you'll see this figure again. Our first question is about the superglacial lakes on the scale of years, and specifically whether the size of these lakes responds to any variability in the environment. So for instance, if we have a high melt year or a high snow year, do we see this response in the size of the superglacial lakes? To answer this question, we use remote sensing, by which I just mean pictures from space. And over the course of the season, the lakes behave in a sort of predictable pattern. Before melting starts, we have zero visible surface water. Once the melt season begins, surface water, that is the size of the lakes, gradually increases. And when the lakes get big enough, they cause the ice underneath them to fracture, meaning that the lakes drain rapidly to the base of the glacier, and our surface water declines precipitously. So this is an idealized model, but what we can do is look at imagery over time and generate a time series that looks like this. So as you can see, starting in about 2018, when we have enough data, you can see this characteristic sawtooth pattern of lake growth and decline. We were interested to know whether the size of the lakes corresponded to variation in precipitation or temperature. And so we tested out a bunch of different indices, and the answer is not really. Instead, we can look at these data by stacking all these triangles on top of one another. And what we can see is that the peak visible surface water, which we can think of as a proxy for the drainage date, occurs far later in the year that had really large lakes, meaning that lake size is less a product of variability in the environment and more a product of drainage date, that is, how long the lakes have to get big. Now, this seems kind of intuitive, but it does mean that lake size is instead a product of ice dynamics, which sort of lends itself to our next question, which is how quickly are these lakes filling and draining? We're interested in this not only because it helps us constrain meltwater movement over the course of a season, but also because, as I mentioned at the beginning, rapid lake drainage can cause a flux of water to go to the glacier bed, resulting in ice speedup. So we can think of that idealized triangle, and we can look at this over the course of a single season. To do this, we use pressure transducers. This is what it looks like in real life. These measure lake level. You can see in the circle, the pressure transducer is mounted via a stake to the lake shore. And if you squint, you can see a string that's attaching to the pressure transducer in the lake. These give us a record that looks something like this. And what I want to draw your attention to here is the coincident drainage of these three lakes that we see. So you can see these structure for motion models made with drone imagery. But the main takeaway from this is that while we did see this rapid coincident drainage of lakes, we didn't see a velocity increase, both with our field methods and with remote sensing. This means that potentially this water is draining into an efficient subglacial system that's capable of evacuating the water in an efficient way. Okay, so that's the lakes, and now we're going to shift and talk about water stored in the snow. And to answer this question, we use ground penetrating radar. Thanks again, Renee, for setting this up for me. So this is what a radargram at the site might look like. So we're imaging the subsurface here, and we can see these two distinct layers that we interpret to be the top and bottom of the water table, abbreviated here as WT. So we can map the thicknesses of the water table across the lake area. So those contour lines indicate the lake basins. And as we can see, there's some distinct spatial variability in the thickness of this unit. I want to also call your attention to the fact that we have surveys from 2 different years, 2 weeks apart. And if we map the depth as a distribution, so the distance to this water table top, we can see that 2024 is much deeper than 2023. This makes sense because it's earlier in the season, so there's still more snow on top of it. However, if we instead look at water table thicknesses, so the difference between these two layers, we can see that the distributions are actually very similar, implying that perhaps there's some temporal stability between different times of year and different years here. Okay, so this is water in the snowpack on the scale of a season. And I want to zoom in even more and think about water change in the snowpack on the scale of hours to minutes. And to answer this question, we can use terrestrial radar interferometry, which is a mouthful, but it's a cool tool. So I'm going to take a moment to explain how it works. This is what the instrument looks like in real life. You can see it's positioned up high overlooking the lakes. And we can imagine waves being sent out from the top antenna and then being received again by the bottom 2 antennas. So thinking of this as a diagram, we can imagine that we're sending out waves to some surface at time 1. And then over the course of several minutes, let's say that that surface has moved away from us slightly. This means that the waves will have shifted a little bit, and we can quantify this amount of shift and interpret it as surface displacement. This means that we get really, really precise measurements on the scale of centimeters to millimeters and on the scale of minutes about the way our surface is changing. And so we can look at this map of surface displacement over the whole glacier. So we're shifting 90 degrees from that satellite image that we saw. You can see the superglacial lake basins as noise because you have a lot of lake ice floating around. But what I want to draw your attention to is this area of red near the margin of the glacier. This means an increase in phase, meaning our surface is moving away from us. And we interpret this to be melt-induced surface lowering. We think that this is preferentially happening on this side of the glacier because it butts up against a steep, dark-colored wall that we think is absorbing a lot of energy from the sun, re-emitting it, and causing the preferential melting that we see here. And again, this is on the scale of less than an hour. So phase shift isn't the only thing we can record with terrestrial radar interferometry. We can also measure pixel stability between acquisitions. You can think of this as sort of how well correlated successive acquisitions data are to each other. And so this is what a coherence image looks like. You can see high coherence in yellow and low in pink. And an example of this is that you can see this sort of thin pink line going down the glacier. This is a snowmobile track. And so you can think about the pixels being physically disturbed, the snows being disturbed. Again, this is about this much change, and this is on the scale of an instrument that can measure this accurately at the scale of kilometers. So this is pretty cool. So we can also map over time what these values do. And as you can see, we see this pretty steep decline over the course of the day, which is a signal that we associate with surface melt. So this instrument has a lot of applications in these temperate glacier environments to characterize surface change. So as a reminder, our goal was to understand glacier surface water dynamics on a range of timescales. I presented a bunch of data. We can see that lake size is more a product of drainage date than environmental variability, that we saw coincident drainage of 3 lakes without a resultant velocity increase, that we see variable water table thickness in the snowpack, And lastly, that we can see these discernible signals of surface change with terrestrial radar interferometry. So I will leave my conclusions here. Just a quick plug, I want to add my voice to those that have been supporting the Union Rally on Thursday, and I'd be happy to take any questions. Yeah, Miranda? Good question. So I showed that time series, and for all of the ones that weren't the really big lake year, it happens mid-July-ish. What controls the drainage physically is when the water is heavy enough to hydrofracture the ice beneath it. Our structure from motion imagery indicates that perhaps the lakes are fracturing in the same place. But as for why that one year was much later than the rest, it's a little bit unclear. There's also some signals that potentially the 3 lakes that I showed are hydrologically connected since they drained all at the same time, but the big lake didn't. So potentially we have these 3 being connected and the big one not. So more work needed. Question. Yeah, Dan.
Do you know what the year-to-year evolution of the internal water table? It's like, is it there year round and it grows and shrinks, or does it develop over the course of a year, like over a melt season?
Yeah, good question. You're speaking to the fact that we have 1 data point per year. My assumption is that it goes away completely during the winter because temperatures do drop below 0, and that it develops over the course of the season. But perhaps it's a quick development and then a stable water table over the course of the melt season based on what we see here, just with that 2 weeks of difference. But ideally, we'd have more data points over the course of the season so we can get more at that temporal evolution.
Very impressive. Have you also tried any kind of tracer studies? Putting tracers in the water, see where they end up?
Yeah, that's a great question. We haven't at this site. It was one of the ideas floated around amidst the many data sets that we collected. There is a perglacial stream that's somewhat accessible, so potentially future efforts could try to see if we see quick evacuation of that lake water from that perglacial stream. Thanks so much, Tahi. If you have more questions. Thank you so much to our speakers. If you have outstanding questions, please find them at our break with refreshments in room 307, and we will reconvene at 10:30 for the next session. And I'm excited to introduce our first presenter, Olivia Olson, who will be talking about human-bird relationships at Fraser Point in Wabanaki homeland.
Thank you, Tahi. I'm just trying to, ooh. Yep, so I am giving an abridged version of my defense presentation, which I gave on Monday. It was very exciting. Thank you to those who came from here. But I today will be telling you about, as Tahi said, human-bird relationships during the ceramic period in Wabanaki homeland, doing that through a case study at the Fraser Point site on the Schoodic Peninsula. The inspiration for this study came from a 4-day workshop held at the Schoodic Institute called A Million Sunrises at Schoodic, Training and Research on the Muted Histories at Fraser Point. If you were here for the faculty lecture yesterday by Dr. Newsom, you heard all about Fraser Point. This project fits within the broader climate change and cultural heritage research that Dr. Newsom takes on there. This was held at the Schoodic Institute in 2022. And the workshop really brought together a diverse group of participants, including academic archaeologists, Wabanaki community members and representatives, and archaeologists, and park staff, as well as cultural resource specialists. And from this workshop, we came to several different research avenues for the collections at Fraser Point, one of which focuses on this bird bone flute found at the site during 1970s excavations. Both archaeologists and Wabanaki community members, and all of the above, had questions about this flute, including how old was it, what kind of bird did it come from, and also, why aren't Wabanaki community members better informed about this item and other material culture from Fraser Point? It really struck a chord as a pun that I do intend to make. And some of these questions we had vague answers for. You know, the swan was large, it probably came from a tundra. The flute was large, it probably came from a tundra swan, and the bone that was used to make it was an ulna. And we kind of know rough time periods from the Fraser Point site. One occupation period was likely 2,000 years ago and older, and then another 1,000 years and younger. But this kind of left us with more questions. We had these answers, but we wanted to learn more about the birds and the flute at Fraser Point. And this is kind of what we were working with. In the box here, we have the extent of the bird identifications that came from the 1970s studies of the material. And this research paradigm, the lack of information that we have on bird bone in coastal archaeological sites is pretty typical of the area. So the problem for us here was that the assumption for that birds were insignificant subsistence items and the lack of integration of other resources such as ethnohistoric records has led to a large gap in the regional archaeological data set. We just didn't really know much about birds. So the goals of this research project were to, one, contextualize human-bird interactions within culture histories and late Holocene climate change in the region. Two, to assess subsistence and non-subsistence uses of birds using an attribute analysis on bird bone tools and by integrating these ethnohistoric records. And three, to establish the first zooarchaeological baseline for the examination of birds in the Gulf of Maine. And this brings us back to the case study and the present research question, which asks, how does the avifaunal assemblage at the Fraser Point site highlight past and present Indigenous values concerning human-animal relationships? And to get at this question, I applied 3 different methods using a transdisciplinary methodology, one that combines many diverse disciplines to ensure high quality research. I used a faunal analysis, traditional faunal analysis, where I identified all the bones and counted them up and did some other statistical things with them. A bird bone flute comparative attribute analysis, as well as an ethnohistoric analysis, reviewing both Wabanaki oral histories, place names, and language, as well as historic records from early European contact. And from the avifaunal analysis, we found that even in a small collection, such as that from Fraser Point, we found a high diversity of birds, indicating a lot of different activities happening with a lot of different birds. Here, this graph shows you the abundance of ducks in the sample. A third of the identified specimens were eider ducks. We also found great auk, extinct great auk, loons, cormorants, 1 eagle bone, and a gull bone. And with the modified objects, we found that bird bone was only used for 1 determinate object, which could also be a flute, as well as the bird bone flute out of 38 total bone tools. Diving into the flute attribute analysis a little bit, we found that the styles and the manufacture of the flutes across the region were very similar, indicating continuity in manufacturing technique, desired shape and functional performance, and that the cultural periods of the bird bone flutes of the region, we studied 20, range from the late archaic to middle ceramic time periods. So quite a range of time. And they came from geese, swan, and duck wing bones. And in the ethnohistoric analysis, we found generally that Euro-American records indicate hunting and cooking strategies and seasonal patterns, whereas in Wabanaki oral histories, place names, and language, they describe birds as important actors in origin stories, giving moral lessons, as well as sustenance, feathers, and bringing seasons back, like summer, which we are desperately waiting for now. And this is another example of some of the ethnohistoric analysis that I did with naming conventions. I'm just going to leave that for a minute. I'm not really going to go into it because I don't have that much time. But I wanted to bring us back again, knowing our results, back to our research problems and goals. And it is to contextualize, assess, and establish a zooarchaeological baseline for the examination of birds in the Gulf of Maine. And to do this, we have to step back in time a little bit. Zooarchaeologists use faunal records to indicate changing climates and cultural systems. And with the birds, we found that a diverse group of birds were used for diverse purposes at the Fraser Point site during this ceramic period. That birds were probably harvested most intensely during spring and fall migrations in an ecological patchwork, and that this analysis sits very well inside the previous analyses on occupation periods. We also assessed non-subsistence relationships using archaeological and ethnohistoric records, noting that birds were used as food, teachers, bone and feather providers, messengers, weather forecasters, guides, and musical inspiration. And finally, we established the baseline for birds in Wabanaki pasts in their use through the archaeological record as well as the ethnohistoric record. And to conclude, we find that the flute found at Fraser Point provided the window and a pathway that research partners wanted to investigate. This changes our understanding of birds in regional archaeological contexts and also adds a data set for others to build upon. I think that I will stop there with my future research directions and thank yous. Thank you. Yes.
Are any of the flutes still able to be played? Has that been considered or tried by members of the community?
Yes, so archaeologists have done that, not members of the communities so far. But one of the future directions of this work is hopefully to integrate contemporary flute and music making practices into future research, which would be great. There is some functionality, I think, that has been conserved. Unfortunately, the Fraser Point flute is broken and will continue to break. Emily Blackwood took a 3D scan of it and is planning on 3D printing so that we can kind of test functionality and see what's going on.
Imagine somebody's tried to make one from a modern bird bone and see if it makes noise, which it must.
Yeah.
But it makes me wonder what about the long-term history of flutes in the world and in North America. Do we know anything about that?
Yeah, so the oldest musical instruments we think are some flutes. They stretch all the way back to the Upper Paleolithic, so 50,000 years ago, maybe, and are made out of, I think that the oldest one is contested, but potentially the oldest one is made from a juvenile cave bear femur. And it was found in a cave, like a lot of other flutes from that time period are, because it's a long time ago. And caves have good preservation. Other very old flutes are mostly made out of bird, actually, or ivory, mammoth ivory.
In East
Crane,
America, are there a lot in North America?
there are a lot in North America. There's several from the Southwest, made of raptor bones. There are some from Mexico and others in Peru, as well as one of the oldest in North America is about 7,000 years old from Labrador. So that was included in this study actually. And what's amazing is that the style and shape and function is very similar. It's conserved over thousands of years.
Interesting.
So,
Thank
yeah.
you.
Thanks.
Right, thank you, Olivia. And if you have more Next up, we will hear from Mari, who will tell us about ice thickness in Eastern Alaska. Hi, everyone. I'm excited to talk to you today about comparing measured and modeled glacier ice thicknesses using Jarvis Glacier in Eastern Alaska as a test case. So first of all, we know that Alaska has over 27,000 glaciers covering approximately 90,000 square kilometers of glaciated terrain. That's a lot of glaciers. How do these glaciers impact climate and sea level rise predictions in Alaska? But also, how can we study all of these glaciers in enough detail to validate our predictions in a meaningful way? Zooming out even more, we know that ice sheets, glaciers, and other land-based ice make up about 75% of global freshwater, but glaciers are expected to lose up to 41% of their total mass by the year 2100. Additionally, Alaska's glaciers account for approximately 25% of current total ice mass loss outside of ice sheets, and they're the largest regional contributor to sea level rise currently. But there's some uncertainty there. Because this is so variable, there are so many glaciers, we don't know the total water volume of alpine glaciers, and therefore the potential impact on sea level rise. To do my part in reducing some of this uncertainty, I'm looking at two study sites over my master's. One, the Juneau Ice Field in Southeast Alaska, the other Jarvis Glacier in Eastern Alaska. This talk is focusing primarily on Jarvis. So Jarvis Glacier is a small alpine glacier, singular glacier about 8 kilometers long and 1 kilometer across in a semi-arid continental climate in the Eastern Alaska Range and alpine environment. There's a lot of data here. It's been part of a large field effort by UMaine Earth and Climate, CCI, and lots of other collaborators. Between 2012 and 2017, there have been all kinds of different studies ranging from the small to the large scale. A lot of ground penetrating radar data was collected there. It's never been used for an ice thickness study, so this gives us a unique opportunity to compare ground penetrating radar, primarily collected by my advisor, Seth Campbell, and then numerical modeling from remote sensing. So my colleagues have done a great job talking about radar, but very quickly, so we're all on the same page, I want to just share the schematic made by my colleague Emma Skelton that shows how this radar is working. It's a common offset system with one transmitter and one receiver. The transmitter sends radio waves into the ice, which propagate in an expanding cone until they hit a material of a different electrical property. That in this case, the bedrock, it bounces off the bedrock, goes back to the receiver that's been listening for it. And over time, we can, by dragging this through space, we can collect an approximation of the depth to bedrock and therefore the thickness of the ice. So that's radar, and then the model. I did not create the model. Our colleague, Daniel Farinati out of the University of Zurich created a conservation of mass model, more on that in a second, to approximate glacier ice thickness. There are inputs of a digital elevation model, the shape of the glacier, and principles of ice flux, and put out a nice raster file that can be used in any geospatial processing software. Some strengths, has a really complete data set over Alaska. That's great, that's what we're looking at. And then it uses in situ radar data to inform the model where available. Since we're interested in radar, this allows us to do some better comparisons as well. Some weaknesses though, they estimate this approach could have uncertainties of up to 30%, which is pretty large across a glacier. We're trying to reduce some of that. So conservation of mass model, we know from physics and chemistry that matter cannot be created or destroyed. It's the same thing on a glacier, but in this hypothetical glacier, we have a hypothetical cross-section A. All ice that flows from and through cross-section A also has to flow through cross-section B, but there's a little more to that. A glacier is a very dynamic system, and there's a lot going on at any time on the glacier as well.
So there's accumulation of mass, so the addition of mass through snowfall primarily across the glacier, including between these two cross sections. There's ablation, melting, removal of snow and ice, and there's also the velocity profile. So what's going on here is at the top of the glacier, there's not a lot of mass and it's normally cold, frozen to the bed. The only way the glacier is moving is slowly through deformation of individual ice crystals. That changes as you move further down along the glacier. That deformation is still happening. But as Tahi and Renee and Kaylee all talked about, there's water in the glacier, there's water beneath the glacier, and that allows it to flow a little faster, in addition to all of this extra mass that is now providing extra driving stress. So any change in velocity there is also corresponding to a change in ice mass. That's our conservation of mass. And then any change in ice mass corresponds to a change in ice volume over similar cross sections. And that's what this model is doing across the across like individual parts of the glacier. It's approximating the cross section at all of these spots and allowing it to calculate the depth to ice and therefore ice thickness. So very quickly, I'm not going to go through all these methods because I don't have the time, but this is what I'm thinking about as I'm processing radar data and doing some geospatial processing. What you need to know from this is that our GPR data is in one form and our ice thickness model is in a different form. And I just need to do a little bit of processing so I can put them in the same format and then run statistics. So here are some of our statistics and results. Starting off, to orient you, it's a bird's eye view of Jarvis Glacier with the with ice thickness modeled on the left and measured on the right, as shown on our radar tracks. We have lighter colors in white or blue and darker colors in shallower thicknesses in lighter colors, and then darker colors are deeper thicknesses. We can see some of these look pretty similar, some of them look different, but we're going to more directly compare them. What I have here is offset along the same radar track, so that's just the difference. I subtract measured minus modeled. And so in this case, anything that's in pink here is a model underestimate, meaning that the ice, it's a positive value. The ice thickness that we measure is thicker than what the model predicts. Anything in green is a model overestimate, meaning that the model estimates that the ice is thicker than we actually measured. And anything in white or close to white is relatively similar between the two. Looking at that a different way, we have I have a distribution plot of offset on the x-axis and then just the density on the y-axis. And this is for all of our GPR data across all lines. And what we have here is actually a relatively normal distribution centered close to zero. So that means in this glacier overall, the model's relatively spot on. That's great. There's a slight trend towards overestimating the true ice thickness, but overall, I like where this is at. However, when I started processing the different individual lines, I noticed an interesting trend between the longitudinal profiles along the long axis of the glacier versus the cross-sectional along the short axis of the glacier. So in our longitudinal profiles, I found that the model overestimates the majority of this data. So the ice is thinner than expected on about 66% of all longitudinal data points. You compare that to the cross-sectional profiles and we find the opposite. The data is skewed in the model underestimate direction, meaning the ice is thicker than expected on 73% of cross-sectional GPR data. So overall, ice is thicker than modeled in cross-sectional profiles, but it's thinner than modeled if you're looking at longitudinal profiles. And why do we care about that? Because our model relies on glacier cross-sections. If you remember my schematic from earlier, the cross-sections are a lot of what's going into how this model is predicting ice thickness. So that's a pretty big deal here. And our understanding of the model accuracy changes depending on the location and orientation of our GPR data. So in conclusion, we find significant discrepancies between measured and modeled ice thicknesses in longitudinal and cross-sectional GPR data. On just this glacier, there are other glaciers to look at and see if that continues on. And then there are implications for evaluating ice thickness in the model accuracy generally throughout this model and other GPR profiles. So thank you to everyone who's listed on here and not listed on here, and I'll welcome any questions.
Mr. Mari?
Those discrepancies you found in the model, is that just based on how the model was coded, or is that just particular to this particular glacier that you used it on?
I'd have to look into that a little more. I think it's like the radar profiles can be picked any way you want. So it could be anything from human error and me picking the wrong line, or the model not understanding what's going on at the depth because it can't see what's going on underneath the glacier.
How does the model look out for potential error taken during the measurements? For example, differential speed in pulling the sled.
We correct for that actually. So I'm not sure if the model is looking at that for other radar data, but for us, we've distance normalized all of our radar profiles.
Thank you, Mari. Next, we have Bailey McLaughlin talking about life stages of trees.
Hi, everybody. I brought my own slide advancer, so we'll see if it works. My name is Bailey McLaughlin, and I'm going to present some work from my dissertation that I'm in the process of finishing and writing up, that I'm working on with my advisor, Brian McGill. So I figured we could start at the end, and kind of the main takeaway from this project is that what we think we're finding is the realized climatic niche of US trees is broadly conserved across life history. So how did we get here? Well, like most of us, we started with a question, a pretty broad question, which for our purposes was, at macroecological scales across coarse climate gradients, does a species' realized climatic niche differ across life history? And in the coming slides, I'll kind of get into how we approach this and what we mean by this in particular, but kind of the answer to this question has important relevance for basic and applied research, helping us understand a kind of species' inherent ecological tolerances, their biogeographic contexts, and how we kind of operationalize that understanding in more predictive and applied contexts for things like management and conservation decision-making. So hopefully you're feeling convinced that this is an important question to ask. And to really dig into it, we have to kind of understand and walk through what I mean by the realized climatic niche, which is kind of the crux of this whole analysis. And so when I say the niche, I'm going to be referring to the realized climatic niche, which is a component of the Hutchinsonian niche for those ecologists in the room. And Hutchinson really suggests that the ecological niche of a species has two component parts, a realized niche and a fundamental niche, which very broadly, if you put those two together, describes the complete set of abiotic and biotic conditions that enable a species to survive and persist. And so the bounds of that entire Hutchinsonian niche are pretty elusive and difficult to define, but an aspect that is pretty readily measurable in a multi-species context is the realized climatic niche, which describes a set of climate conditions in which a species can and does survive. Also, just a shout out to the ecologists. Some people refer to this as the Grinnellian niche, but I'll call it the realized climatic niche or the niche for shorthand. And so if we boil this concept way down, we can look at an example species and kind of measure its distribution in simplified two-dimensional climate space along axes of temperature and precipitation shown here. And if this polygon is meant to represent this pretend species realized climatic niche space, or the combinations of temperature and precipitation in which this species is known to survive and occur. And so for the reasons I started us off with, it's really important for a lot of ecological applications that we get this estimate right and that we're accurate in our measurements. But most efforts to map, measure, model, estimate this niche polygon rely on adult or age unspecified distribution data to kind of inform these estimates. But what happens if your climate tolerances change as you mature from a juvenile into an adult? How does that impact the bounds of that polygon? Do they change? And so trying to understand this is really what drove the question I started us off with, which is very broadly, does a species, in our case trees, realize climatic niche change across life history? And so there's some kind of starting points to try to understand this. And so another ecologist named Peter Grubb, also back in the 70s, in the 70s, suggested that species have distinct regeneration niches, which are supposed to be kind of separate from their adult survival niche. So if we put that in the context of the realized climatic niche that I just described, this would suggest that juveniles of a species have more restricted climate tolerances than their adult counterparts. So again, we can visualize this in a simple schematic where we have an environmental variable, pick your favorite on the x-axis, and then probability of survival on the y. And if we look at the seedling survival curve in blue here, we can see that seedlings survive in a narrower set of climates compared to saplings in gray and adults in green. Visualize now in our two-dimensional climate space, simplification, temperature and precipitation are axes now. Maybe it looks something like this, but in this case, in both cases, you can see that the juvenile niche is kind of nested and subset within the older life stages. And so trying to understand whether or not this pattern is typical in a multi-species context at kind of range-wide continental biogeographic scales is really what drove my interest. And that's where the macroecological component comes in. And so to start to address this, we use trees as a model organism, model taxon, and I extracted geographic occurrence data from the Forest Inventory Analysis database for 200 trees, just about 200 trees, and partitioned that geographic data into life history stages, which you can map in geographic space, something like this. And then for each of these geographic points, we paired climate data for 3 climate variables of broad ecological relevance to trees to make our analysis across species comparable. And those were prolonged heat stress, drought stress, and frost stress. And so we can use these variables to extract a 3-component climate coordinate that corresponds to each point in geographic space and ultimately map that in corresponding environmental space. And so these polygons are meant to represent our realized climatic niche estimates for a single species across 3 life stages along our axes of interest. And so when we do that with real data for a walnut here and a spruce here, it looks something like this. And so they're probably too small to read, but these are our climate axes. And essentially, these point clouds are our data-driven estimates of the realized climatic niche of these 2 species. But we did this for 215 species. And once we kind of map and describe the niche in that way, we can start to compare similarities and differences between the different life stage clouds. And so what we did to quantify the niche, again, these are the 3 axes I measured, but I'm going to walk through some of the metrics in simplified 2-dimensional space again, because it's hard to visualize in 3D. So if you look at temperature and precipitation and look at a pairwise comparison of saplings and seedlings, and these are our 2 niches, we can start to measure similarities or differences between these by looking at things like differences in the niche center, which there's going to be a temperature component and a precipitation component, changes in niche boundaries as minimums or maximums along each axis, and changes in niche breadth with this kind of just spread along each axis. And in a few minutes, I'm going to show you the data for changes in niche centers and breadths, but we also looked at the boundaries. Okay, and so once we did that, what we found was at the scales of our analyses, these kind of multi-species, large spatial scales, measured along 3 distinct climate axes, niche centers and niche breadths seem to be pretty consistent across the 3 life stages. And niche boundaries, which I won't show you data for, are broadly similar as well. And so now that I've told you that, let me show you. So this is going to be, the first set of graphs is going to be for the niche center data, and I'll walk you through the orientation for one, and then I'll just kind of click through the rest, because they'll all be oriented the same. But we're going to look at the adult sapling comparison and the sapling to seedling comparison. The x-axis is going to be our climate variable of interest for the metric we're looking at in the first few graphs center. And my MO is frequency histogram, so you'll see a bunch of those where a number of species is on the y. And so here's the data for summarized for 215 species. And the dashed line is the median of the distribution, which in this case is centered on 0 and kind of evenly spread around, indicating that there's little difference in the niche center along this axis for these 2 comparisons. And now I'm going to kind of rapid fire through the rest. So now if we look at prolonged heat stress, similar pattern, centered close to 0, even spread around, and drought stress, not so different. And now if we kind of click to the niche breadth, again, you'll see the same orientation. Now the x-axis is going to be the same three variables, but the measure is a log ratio, so the distribution will be centered on 1 instead of 0. And similar patterns, slightly offset 1, but that's what our frost stress looks like. And I'm labeled that one, I think. And here's colon heat stress, and here's so again, the result we find is at these scales, kind of broadly similar center and breadths across lake stages, and boundaries are similar. And so what we take that to mean is kind of going back to where we started. So that very first point on the title slide, we interpret this to mean that the realized climatic niche of trees remains relatively stable across distinct life history stages. So at this scale, we don't see distinct evidence for a regeneration niche, which doesn't mean that the regeneration niche doesn't exist, but there's likely a scale dependency in it, since we're not detecting it at these large scales. And so in our macroecological test of this theory, we find inconsistent support for what we often take as kind of like a dominant prediction of the discipline. Okay, so lots of people to thank, primarily Ryan and my committee and peers, and Brunel, the niche theorist turned solidarity dog, would like to invite you all to a rally next week. How fast I talked.
We have time for questions for Bailey.
Yes.
Yeah, for those of us who aren't foresters, is the age of seedlings, saplings, and mature roughly the same for those 200+ species, or is it variable?
Yeah, good question. Also not a forester, full disclosure, but it's a coarse approximation, and we basically use what the data set that we use there, kind of broad classification. So it's going to be imperfect for each individual species, but broadly kind of they use size as kind of an age proxy in the data. So
what's the age range set for those three categories?
So if I had to estimate, seedlings are probably like a few years on the landscape, saplings a few decades, and adult trees more like 100 years. Yeah.
Thank you.
Yes.
Other questions for Bailey?
Yes.
So my understanding, these studies were done in a group of trees that were mixed age, mixed species.
Yeah.
So do you think you would get a different answer if you were looking at seedlings, like trying to recolonize a clear cut area? Because that, recently there's been a lot of talk about how trees help each other share resurface underground. Like how much of a factor is that in the niche that young, vulnerable sapling could survive versus in a mature forest where everyone's cooperating?
Yeah, so I think that's a good question, and I'd probably have to think a little bit more deeply about it. But I think that's kind of where I was making the point about the scale dependency. I think if we looked at more local scales, at kind of a regional area, we might see different patterns because of other dynamics like succession and things like that. Potentially also if we looked at this through time, which this is a spatial test of the regeneration niche idea, there could be a temporal regeneration niche at this scale. It's just not what we tested here. So I think that potentially, and basically what we did was try to take a contemporary time slice of data, and this is at like the continental scale of the distribution. So some of that noise I expect to kind of come out in the wash, spoken like a macroecologist, I think, but yeah, I think it's possible and just not kind of the focus that we had for this project.
Thank you, Bailey. Next, we'll hear from Roisin Rumsey about hyperspectral images of ice cores.
All right. So, like she said, I'm Roisin. I'm going to talk at you a little bit about hyperspectral images. A small preface. I have a background in computer science, not climate science. I've learned a lot in the past couple of years, but if I say something super wrong or that doesn't make any sense, I apologize in advance. So I think at this point, you guys know what ice cores are. I'm not going to dive too much into that, but I do want to show you what happens when instead you just cut a slab, flat both sides, and you take some pictures of it. So this is North Grip image with a line scan camera back in 2005.
And what a line scan camera does is it captures just one row of pixels at a time. You have a moving sample or a moving camera. That lets you get really high resolution image. And that lets us see these annual layers here. And that means you could stand there and count the stripes, count back the years. Don't do that, that would take you too long. So this was in 2005. Our technology has advanced just a little bit since then. And now we have the only hyperspectral imaging system for ice cores. This is a lot, I know, it's okay. We're gonna break it down. In that top right corner, you're gonna see an image at a single wavelength. And that's what you'd get from your line scan camera. What my system does is it sees across the visible light spectrum, as you can see down there, and into the near infrared. And it will take not just one picture, but 224 pictures across the wavelengths from 400 nanometers to 1,000 and stack those together. So what you're seeing in each pixel, you get a good sense of what that sample is doing with the light across that spectrum. So now that we've upgraded from traditional line scan to hyperspectral imaging, we still have fast access to data. You can scan a meter of ice in about 3 minutes, and it's still non-destructive, so you can put that slab right back into the archive. But now we have all the spectral data with those extra 223 images. So you can think of it like upgrading from your black and white TV to a color TV. You see a lot more, you have a better understanding of what's happening. So the way we do this is we have our sample of ice, it's about 3 centimeters thick, moving in front of our camera. And we have 4 lights, 2 on the top, 2 on the bottom. 2 on the top are only at half intensity, while the bottom ones are at full intensity, and they're angled at 45 degrees. And that means if there was no ice there, or if the ice was completely transparent, the camera wouldn't pick up anything. But because of all this impurities that we have in the ice, it's refracting that light. That's what the camera's picking up, as you can see from the image on the right-hand side. That's our ice core. And we also use this reflective imaging technique where, as you can see, it looks a little different on the right-hand side. But that means we just have the 2 top lights at full intensity, and what the camera's picking up is how that light is reflecting off the ice. And this is the more traditional way that people use hyperspectral imaging, because the way that the light reflects off of a sample will give you this spectral fingerprint and tell you what's there. But since our ice is transparent, it's a little harder to do with just top lights. So I started looking at my images, realized we had all these bubbles, and kind of decided that was in the way of our actual data, and we just wanted to throw those out. That's the nice thing about having digital data. You can just edit it like that. But instead of throwing it out, we want to share with our collaborators, because some people really care about bubbles. I don't know why. So I have developed some algorithms that are going to detect how the light differs with those bubbles compared to the rest of the ice around it. So you can see it created this binary image where your ice is black, your bubbles are white, and then another algorithm that drew these red ellipses. As you can see, the arrows are pointing to those, a few of those. And it's not perfect, but it does give you a good approximation of what each individual bubble is kind of doing. And then past few weeks, I worked on this. So this is a graph of Allen Hill's ALHIC 2302. And I was able to go to Denver in the summer and get about 40 sections imaged from 10 meters down to 46 meters of this core. And here I've broken it down by centimeters. And on this left-hand side, I got a good approximation for how many bubbles were in a square centimeter moving down. And what this variation is telling you is that you might be seeing a change in temperature, a change in snow accumulation. And then jumping all the way to the right-hand side, you have average orientations down those centimeters. And that is going to suggest a dip in the layering. And the nice thing about that graph there is one of my collaborators was working with electrical conductivity measurements of this same core at those same depths. And what they discovered was, I think there's a 70-degree dip in those layers there, which seems to fit well with our graph. So now with those bubbles handed off to my collaborators, I can get back to looking at some layers. And there's still a lot of work to be done there because I just finished up with the bubbles and our nice little side quest there, but hope you enjoyed this update. So. Yeah.
How much time is involved in the 36 meters that you sampled there?
Well, just for imaging them, I mean, that's 3 minutes.
How much time is represented in the end?
I do not know that.
Because there were very interesting patterns in the bubble, so
Yeah.
what does that mean?
That's what I'm looking to find out. Yeah.
I'm just wondering the scale of time of those variations, that's sort of a key thing.
Yeah, I'm not sure I can tell you, sorry. Yeah.
This peak, would you expect to be able to see differences in layers like volcanic events and ash being collected, or even organisms within the ice, or what layers do you expect?
Well, with this one specifically, you can see in the middle of this ice core, that's their bright little strip, and that is volcanic ash. And so that's something that's going to show up in our spectral layering. So yeah.
Thanks, Rashid. Next, we'll hear from Allison Berry, Allie, about fjord dynamics and icebergs in Greenland.
Yeah, hi everyone. I'm super excited to share some updates with you about the icebergs in Northwest Greenland. Before we dive in, I'll get us all on the same page about why we care about icebergs in the first place, or why I specifically care about icebergs. And that's because icebergs are currently not well represented in Earth system models. And I think that that's kind of problematic because I would argue that icebergs are indeed an important part of the Earth system. And I say that because they account for up to 50% of the freshwater flux from the Greenland ice sheet. And along with the other 50% of liquid water runoff, these icebergs can obviously add to sea level rise. But differently from the liquid water runoff that happens at the ice sheet, icebergs infamously end up in the middle of the ocean where they become shipping hazards. And that's because they move away from their source. So this map here is showing us the solid ice discharge around Greenland relatively, and then all of the ocean currents that surround Greenland. And so as those icebergs break off of the ice sheet and move into these currents, they're constantly moving and melting. And as they're moving and melting, they're injecting their cold fresh water into the relatively warm salty ocean water, which can in turn impact ocean circulation. So hopefully now you all agree icebergs are indeed an important part of the Earth system, the climate system. And so it's a bit of a problem that we don't have them well represented in Earth system models, because as we know, it's these Earth system models that we use for all of our future projections. And if we're missing a big component, our projections are probably a little bit skewed. But the good news is that there's progress in including icebergs from the Antarctic ice sheet into the Southern Ocean. But icebergs in Antarctica are a little bit easier to deal with because you all probably see in the news, they're like huge and they don't break off all that frequently. It's a little bit easier to model them. In Greenland, things are complicated by all of the fjords that stand in between the ice sheet and the ocean itself, which you can see here highlighted in these green areas. And so what's currently happening in these models is that they're injecting all of the fresh water, whether it be solid or liquid, right at that ice-ocean interface, so right where the ice sheet meets the ocean. And in the case of Greenland, that's in the fjords. And so what's potentially happening is we're seeing an over-attribution of freshwater flux in the fjords, while we're simultaneously ignoring any of the fresh water that would be input into the North Atlantic from the icebergs that are big enough to move away from the fjords and enter the open ocean. And so we look at this big picture. The overall goal of like my entire career and probably that of others is to have icebergs realistically represented in Earth system models and fully coupled. The problem with that currently is that fjords kind of complicate this matter and we're dealing with misattribution of fresh water. So we kind of want to understand like, you know, how bad is that misattribution? Is it really far off? Is it not so far off? And thinking about that problem led us to the question that I'll be talking to you all about today. What role do these fjords play in modulating iceberg distributions? And so to answer that question, this project works as a case study and looking at Northwest Greenland, because as you can see in this map here, it has some diverse looking fjords. And as you'll see later, it produces quite a good bit of icebergs and it also has variable environmental conditions, making it a good study site to see what's going on. And we get these iceberg distributions that I'll show you from an automated detection algorithm using Sentinel-1 SAR imagery. And if we look at this distribution of those icebergs for the entire Northwest region that's highlighted here, we get something that looks like this, where we have our seasonal dates down here, starting in the summer of 2017 and going all the way down to winter of 2022. And then here is just the number of icebergs. So we can see that, you know, 2017 was a big year, not sure why. And then moving on after that, we start to see some form of seasonality. But most importantly, what I want you to take away from this is that most of the icebergs in this distribution are small icebergs or icebergs that have a footprint of less than 10,000 meters squared. And so if we think back to that issue of the misattribution of fresh water, maybe it's not so bad looking at this because if all of the icebergs are small, then they're probably small enough melting in the fjords, only a few of them are making it out. But plot twist, I set you up. If we look at the same distribution, but instead of looking at abundance, we look at volume, we see almost like a total flip in contribution, where even though there's so few large icebergs relatively in the whole distribution, those few large icebergs actually make up the majority of the fresh water, which would then indicate that these modeling practices are maybe a little bit skewed, and we should be concerned about these large icebergs that have the capacity to move away and inject their fresh water in the open ocean. So getting back to this question now, what role do the fjords play in modulating that iceberg distribution? We take it a step further and we break down this Northwest region into 6 different subregions based upon fjord geometry, which includes length and depth. When we do that, we end up with 3 broad categories. The first one being medium length, shallow depth, that's regions 1 and 3. And then we have long depth, long length, deep depth, that's regions 2 and 6. And last but not least, we have short length and deep depth, and that's regions 4 and 5 there. Obviously, we are missing a few potential categories, but this is just a case study and hopefully future work will expand to all of Greenland where we'll get a more complete picture with some different fjord categories. So now if we look at that same distribution, we're going to be focusing in on large icebergs, since hopefully we can all agree that those are kind of the important ones in this scenario. When we look at the distribution split up by region, what we see is that regions 2 and 6 make up the majority of the iceberg distribution, again, of large icebergs. So we have our seasonal date here, number of icebergs here, and very clearly 2 and 6 hold the most icebergs, and maybe that makes sense given that they have the most area. But if we, again, we want to get at what role the fjords play, we try to take this distribution and average it or divide it by the average fjord length to get an idea of what it looks like after that. And when we do that, we see a change in distribution where these short and deep fjords actually start to make up a greater majority of the total distribution, indicating that fjords do have some modulating power in these iceberg distributions. And if you have a super great memory or you're intimately involved in my research, you'll recall that I was trying to do a machine learning algorithm to see if we could predict this iceberg distribution using a slew of environmental variables that Sean Burkle helped me get from Climate Reanalyzer. That ultimately didn't work, but I wasn't ready to let go of all that data. So I thought, why don't we look at how these iceberg distributions respond to changes in environmental conditions and these different kind of fjord categories we have. And when we do that, starting with the long and deep categories, we're looking at atmospheric temperature, sea surface temperature, and glacier velocity. And then we have large iceberg volume here in our regions 2 and 6. What we can kind of see is that in terms of atmospheric temperature and sea surface temperature, there's really no response to changes in atmospheric or sea surface temperature. There's no change in the distributions. They don't respond to it. But there is some change to, or there is some response to changes in glacier velocity, especially in NW6. And then if we look at the medium and shallow categories, we see that it does show some response to changes in atmospheric and sea surface temperature, as well as glacier velocity, specifically in NW3. Notably, it's the reverse trend of what we would expect, and I'm open to your interpretations on that. And then lastly, if we look at those short and deep categories, we see that they have some response to changes in atmospheric or sea surface temperature, while they don't have any response to changes in glacier velocity, especially, I think it's NW, the orange one, NW4. So if we pull all that together, maybe we can start to say that these glaciers that are connected to long fjords, their iceberg production is not so closely tied to changes in environmental conditions, but maybe more closely tied to glacier dynamics. While as we get into shorter fjords that are more connected to that open ocean, the iceberg production there is more closely tied to environmental conditions rather than glacier dynamics, with some obvious caveats. I'll leave you with some conclusions we can say for sure and encourage you all to RSVP and attend the rally next week. Thank you.
Questions for Allie?
Is the large versus small differentiation kind of universally accepted for the Southern Ocean and here, or is it specific to your state?
Great question. I don't think in the Southern Ocean, because like I said, the icebergs in Antarctica are just like huge and so rare. So they're like totally different category. But I do know that that 10,000 mark is consistent with some studies that have been done in Alaska, which is, I would say, a more similar kind of fjord system to Greenland. So,
Thank you.
yeah.
As glacial breakdown proceeds, would we expect to see a change in the ratio between large and small icebergs, and which way would you expect that to be going?
Great question. I think that that's part of what this research is looking at, right? And like diving in deeper to like how those glacier dynamics play a role. I think we do know for sure that we expect to see an increase in iceberg abundance with an increase in glacier velocity. And I think that question specifically will be very site dependent, given things like glacier width and whatnot.
Thank you, Allie. Ooh, wow, beautiful title slide. Next, we'll hear from Leo about diatoms and lakes.
Thank you, Ty.
Hi everyone. It's my first time talking in front of all of you. I brought a stage prop. They might or might not use. So yeah, my name's Leo. I'm a second year PhD student with Jasmine. And I came from Chile because I really like diatoms. And I was very interested in what Jasmine was doing in linking neo and paleoecology to better understand really how we interpret diatoms to understand lake ecology and past climates. So my what I'm going to present is what I've been working on the last year, which has to do with diatoms, of course, here in northern Maine, and with a particular genus that doesn't have too much work done yet called Alakasira. So diatoms. It's a shame that's covered up there, but we're going from macroscopic to microscopic with Ali's talk. So these are diatoms. This is a diatom. It's a microscopic phytoplankton, kind of like this, but in actuality, it's much smaller. I like putting it up this size though. You can see it has a very ornate cell wall. It's made of siliceous material, kind of like glass. And they're great because, sorry, I forgot about this. So that's what a live phytoplankton would look like with its chloroplast. And that capsule would correspond to one of these cells. And I think diatoms are great because they're very abundant, they're very diverse, and they make great fossils. To make it more relatable, you might have seen diatoms in your backyard using diatomaceous earth, which is a pesticide. It comes extracted from ancient lakes layers. But if you look with the microscope, you'll see a lot of these buggers called diatoms in there. But my interest is really, again, studying the ecology and linking neo and past of certain groups. So for example, the analogy here I can make is you have a lake and it varies a lot seasonally, like from winter to summer. And you'll find that diatoms will also vary with seasonality in those conditions. Kind of analogous to how you see a sediment core from a lake, which are one of the best climate indicators in temperate regions. And you can see the change in coloration has to do with change in organic matter, which can also talk about climate changes. And there you'll find a lot of fossil diatoms. And you can draw a parallel between colder conditions seasonally with colder climate conditions, as well as summer-like diatoms with warmer climate conditions on longer timescales. And what brings these together is the ecology, understanding what is the ecology of the diatoms now and how we can better interpret them in the past, which means understanding where, when, and how they're living about. There's been some great work that's been done in this front. For example, some groups that can tell us about how long the ice cover period is, or shout out to Jasmine again about small plankton species like these ones that can tell us when lakes are stratified, which means more temperature or less wind, and other species that can tell us about nitrogen enrichment. All important things to understand climate and environment. So what I'm interested is in this diatom that you've been seeing so far, which is called Alakasira. And what happens here is two problems. They have a large size range, as I can show here with these electron microscopic images. You have these long elongated groups and a shorter mantle version. So kind of two flavors, but there is a large size range. And they also these two classes can make longer filaments or chains versus the small class that can make shorter chains. And for Alakasira, the large groups are much more studied. They're much more easy to study, and they've been used in paradigms of understanding climate change, where large Alakasira have to do with mixing conditions, thoroughly mixed lakes, maybe colder conditions, but when conditions get warmer, lakes stratify and the large Alakasiras tend to sink to the bottom. The problem is that the small class isn't really understood ecologically, so they could either, be favored by mixing or stratification because they're smaller, maybe more buoyant. So they're very abundant in sediment cores, but we don't really know what they mean. So it's hard to interpret that part of the past. The second problem has to do with their small characteristic, and their taxonomy is very challenging. Here's an iconography from 2000, not too far ago. And I promise that those are different species, but you can't really tell too much because they all come in this kind of like basic square shape that was first identified as Alagacera distance, but this has become a big problem because when you look a little closer with modern technology, you see this, and everything that everyone else was looking at doesn't look like that. Similar, but still different. And that's probably because it's extinct, since these come from the distance, Alagacera distance comes from diatomaceous earth, which was from the Miocene, so it's understandable that things have changed. And what we see now are these species that people have identified as Alagacera distance. So it's very confusing, and that's another thing to look at with this group. So I guess here the objective is to document the ecology of the small short mantle Alagacera taxa to better understand climate. And I've been working at the northern Maine yoke camps west of Millinocket. Here I'm going to show results for Crawford Pond to the right. And this work here has to do with the broader aim of reconstructing thermal structure in the lakes, because it seems like deeper stratification could be affecting insect populations like mayflies. But here you've already seen Crawford Pond. And what I did to understand where, when, and how is through going to the lake to the deepest part, deepest location. I took environmental data like temperature, light penetration depth, and water samples every 3 meters down the water column. And I did this for 16 days from May to November, ranging from 1 to every 3 weeks in this period. I also gone in winter and we'll keep going, but this is the contemporary part. My first attempt doing contemporary ecology. And in the lab, you count the samples I took for phytoplankton. Those are the large Alagacera, and here are the small Alagacera. You can see that they're very different and probably ecologically relevantly different. And results. So I know it's close to lunchtime, and this might trigger some hormones, but here is imagine a cross section of a lake. You're a big fish, and you're looking at a lake. The water column down every 3 meters. And to the x-axis is every date I've sampled. You're seeing temperature and dissolved inorganic nitrogen. And during spring, you get a very mixed condition. There's no big thermal gradient. It looks more like a smoothie. But as summer comes in, you get a thermocline establishing in the red dotted line, which means stratification, which looks more like the raspberry cake instead of the smoothie. The white is the depth of light penetration. And nitrogen gets trapped under the hypolimnon. But as autumn comes back again, you get the smoothie lake again. All is mixed. And this is very typical dimictic lake for boreal settings. So what do we find? Well, for the big flavor, something typical, they're very smoothie-like, which is they like mixed conditions, but they don't live in stratified conditions. And for the small ones, which we care about, or I'm interested in, we find something different, which is key. They're doing okay during the mixed periods, but they also persist into the summer period, as we can see here, and they follow some kind of depth gradient or depth trend that seems to follow the metalimnion. So the takeaway is that, well, they are different from the bigger size class, and they seem to thrive in the metalimnion and kind of vary along that. Gotcha. And very briefly, I lied. So this is a problem too. I put Alagacera pusilla out there, but this is Alagacera pusilla properly identified, and the spines are a bit different. So I really don't know what I have yet. It could be some variation, but there's work to do. You can see that the trace I did is different. And just a first brief teaser to the past, we took sediment cores from the same lake, and we're traveling back in time through that. And these are just some results that I have so far for the top 20 centimeters. And we can see that they have slightly different trends. That is a large taxa. They increase and decrease throughout this, while the smaller taxa increase, but then maintain stable abundance, as other indicator taxa of stratification kind of increase. So we could be talking about different ecological preferences between the same genus. So yeah, thank you everyone for your attention. I want to thank the Yoke Ponds. They financed this work, the graduate student government, and the Corps for helping me with the data acquisition, and everyone that helped in the field.
I'm wondering, like, if it seems like the morphological differences between the different types that you were identifying seem to me as a human and not a diatom to be pretty minimal. And I'm wondering if those are like adaptations to different environmental conditions, if they're just sort of a like artifact of different evolutionary paths, like why are the spines different shapes?
So there's probably a lot of adaptation that goes on. I didn't mention, but there's about like 20,000 species identified so far. And planktic diatoms seem to be more cosmopolitan, but when you look deeper, they're not, because when you look at this electron microscope level, they're a lot more different than we thought. So it could be very local adaptations. It could be adaptations to the physical dynamics of the lake structure, and they could evolve rapidly. There's cryptic species, so there's a lot going on.
Cool.
George?
You showed that the large species dominates during the isothermal conditions during turnover in the spring and fall. And
yes,
I guess that makes sense because the moving water suspends those larger particles more easily than that would be the case later on. Is that
correct?
Partly right. But there would also be differences in nutrient availability. Do you have any idea how that plays into the story?
So that's another resource gradient that can happen, and it seems like the smaller taxa are more tolerant to oligotrophic conditions, whereas the larger taxa can more readily be found in meso to eutrophic conditions in different parts of the world.
But even on a seasonal, the nutrient availability in the spring is different from in the middle of the summer, for example.
Yeah, and for example, the smaller taxa seem to be just like slightly above where the nutrients are, so they still can tolerate very low nutrients or limitation.
Any other questions for Leo? Next, we will hear from Andrea about something else.
Hello, all. My name is Andrea. I'm your local alpine plant enthusiast. And today I'll be sharing with you kind of a new project that I'm involved in that will be one of my dissertation chapters. And it is titled A Natural Experiment from the Alpine to the Arctic, Evaluating Local Adaptation in Herbarium Specimens Using Reflectance Spectroscopy. So many alpine plant species that we know of across the mountains of the northeastern US and Canada are also found throughout the Arctic. And many of these plants share physiological characteristics needed to withstand the similar, very extreme climatic conditions that they're exposed to at high elevations and also across the Arctic. So a lot of these plants have very prostrate or low growing growth forms, or a lot of these plants also have very thick leaves to protect them from these extreme conditions. However, we're not quite sure how individuals of the same species may differ in their physiological responses across this large geographic range that includes kind of barriers to these populations. And the ability of these plants to locally adapt across this large geographic range could thus tell us about their ability to withstand future changes in climate, as populations with limited abilities to adapt may be forced to migrate or become locally extinct. So some of the things that kind of drive differences in these physiological adaptations or traits are topographic features that influence the climatic variables that these plants are exposed to. So if we think microtopography or microclimate at that scale, at the site level, we might see differences in adaptations between populations of the same plant within the same mountain, or we can also think about it at the ecosystem scale and look at adaptations in the same species across a mountain range. And so why do we care about plant traits? Well, these traits and physiological adaptations can tell us a lot about how individual plants and populations are responding to their environment. And for most of the talk, I will be focusing on leaf traits, but we can also measure traits associated with roots or below ground traits, structural traits like stem density, and also reproductive traits like phenology and also seed related traits. And so there's also a lot of literature that links specific plant traits to temperature and specifically warming. So we can see in this table an example where we see a positive relationship between a very simple trait, plant height, and experimental warming. So this kind of lends itself to the idea of shrubification in the Arctic and the Alpine zone, where individuals might be kind of growing taller in these warming environments. And so how can we learn more about the physiological adaptations in plants across space, but also especially through time? And this is kind of where the project enters like new ground for this field, where we're hoping to use herbarium specimens to better understand the trait differentiation through time and across space. And for those of you that don't know, herbariums often house hundreds of years of plant collections and were originally created for archiving biodiversity and the verification of species identifications. But recent research has also demonstrated that there is a wealth of data within these collections beyond just species level data. And so this is where reflectance spectroscopy comes in. So this is where we are measuring the light that is reflected off of, in this case, leaves. And this tool has become critical in expanding our knowledge about the diversity of traits within an individual plant, but also the diversity of entire ecosystems. And so when we measure the reflectance spectra of a leaf, we get obviously this wavelength, and from this measurement, we can estimate traits. Things like leaf chemistry and structure can be extracted from this data, which is what we are hoping to do with our herbarium specimens. However, normally this is done with live specimens. So up until like very recently, it was unclear whether or not we could reliably estimate traits from herbarium specimens because they are pressed and dried specimens. And this is all research that is happening in the Mireles lab here at UMaine. And so this is the spectrometer we use. It's a field spectrometer. I have hiked this device up Katahdin. It's heavy and not fun, but this time it is living in the herbarium. And basically the spectrometer is a device that is then connected to a lens via a fiber optic cable. And then that lens is what records the light that is reflected off of our specimens. And I'll also mention that the utility of this device is that it is non-destructive. So in the past, a lot of trait measurements taken from herbarium specimens are often destructive. And this is a totally non-destructive way to measure traits from specimens, but also living plants. And so there are a lot of caveats to measuring traits and spectra on herbarium specimens. So these specimens are mounted on a wide range of paper types with a wide range of glues, tapes, and other adhesives. All of these things affect the way that light is reflected off the specimen. And the specimens themselves can be of varying quality. So damage due to their age and storage can affect the spectra that is recorded. And also it is unclear how much older specimens can be used in this research. So that's still kind of an ongoing question we have about, can we reliably measure the traits of specimens from like the 1800s? Unsure. And again, all of these variables affect the reflectance measured by our spectrometer. And so my main research questions are, how do traits in 6 Arctic alpine species vary from northeastern alpine zones to the Arctic? What environmental factors, especially photoperiod, influence this trait differentiation, if there is any? Is there a trend in trait values across time within a species of the same geographic region? And then I also hope to kind of learn about the process of using this method on herbarium specimens, especially with specimens that have very tiny little leaves. And I will show you a photo because that kind of just adds a whole other layer of how this method can be difficult. So these are the 6 species that I'm focusing on. As you can see, they all have very tiny little leaves, which it can become a problem when you're scanning a leaf. Everything that is around the leaf is affecting the light that is reflected back into the lens of the spectrometer. So we're working on ways to kind of use like a pinhole basically to measure traits in really small leaves, especially something like Bigelow's sedge, which has very, very small leaves. And all of these species occur across northeastern mountaintops in the alpine zone and also throughout the Arctic, and most of them have a circumboreal distribution. And this is just kind of an example of their distributions taken from iNaturalist. And so what I'm working on right now is collecting all of the specimens of my 6 focus species within the UMaine herbarium, because not all of them are digitized yet. UMaine has a small but very robust herbarium home to specimens from the 1800s through the 2000s. And here you can just see an example of some of the specimens I have collected of Diapensia lapponica, and they kind of range in ages from like 1923 to about 2001. However, in order to answer all the questions I hope to, I will be traveling to, I will be traveling to a couple different herbariums across the Northeast and Canada so that I can include specimens that were collected in the Arctic and other mountaintops across the region. And so this is just kind of a quick example of a reflectance spectrum graph from a herbarium specimen. And if you remember back to that original graph I showed, it looks a lot like the fresh scan of a fresh leaf, which is great. And that's kind of like my main takeaway for right now is it is possible to measure the reflectance of herbarium specimens and therefore reliably estimate plant traits from these collections, which is like a very new, very cool thing. And just to wrap it up, science is work and science is labor, and a lot of the scientific workers on this campus, specifically grad workers, are living in precarity, as it has been over 500 days that we have not had a contract and we've been in bargaining. And I personally think that in order to do all of this amazing science, we have to take care of the human beings behind that science. So I invite you to RSVP to our rally. And the RSVP is really helpful because then we know we can plan for the correct number of people. So please do that. And thank you to all my funders. And that's it.
Any trends with your structure graphs of how herbariums can better preserve things like using the right water papers or glues?
Yeah, I think the answer to that is kind of there's no one particular like better glue or better paper. It's just there's such like a wide variety that makes it kind of tough. I would say I guess that the newer specimens are all kind of like with older specimens, the paper kind of like is potentially degrading or is exposed to light and it like is splotchy in different areas and that's it kind of stuff. So with newer specimens, at least most of the time, the paper itself is like one color, which makes it easier, but yeah. Yeah.
As you know, I'm sure David Bierling, the British biologist, showed that the density of stomata on the underside of leaves changed from the Industrial Revolution on till now using herbarium specimens.
Yeah, yeah.
And then used that to reconstruct, and that was based on changes in CO2 concentrations in the atmosphere and the need for the density of stomata on the leaf. And then use fossils that in fact came from our lab, among others, of Salix herbacea to reconstruct the CO2 levels of the lake glacial, for example. You've noticed things like that in other taxa? Is that something you're looking at all? I mean, I know Salix herbacea happened to be one that they used a lot. And it shows up abundantly in lower, lake glacial sediments. And not all these do, but are there other ones that show a similar pattern?
That's a good question. I don't think I have the answer to that yet, because this is kind of my initial exploration into this topic. So I think as I am able to look at more specimens, that will, come about. Yeah, this is all very, very new. So yeah.
Something to look at. Thank you.
Yeah, thank you.
Hear about that at Bournes next year.
Yeah.
From Elizabeth Rogers about research as participatory heritage work in Wabanaki homelands.
Thank you. So yeah, I'm Elizabeth Rogers, for anyone who doesn't know me. And I'm an interdisciplinary PhD student, and my background is in archaeology. Archaeology is definitely a focal point of my dissertation proposal, which is what I'll be introducing today. However, I also really kind of stepping back in this and thinking about research more generally, including the kinds of research that many of us are engaged in here at CCI. And that is thinking about research as a process of heritage work. And I'll be doing this through a participatory case study involving Wabanaki pottery heritage. So what do I mean by heritage and heritage work? We might think of heritage as kind of objects or traditions, things we might find in museums or historical places, culturally significant landscapes. However, we can also think of heritage as a process, as the ways that we connect with those cultural items to create a sense of connection to the past, to understand how we identify with that past in the future, shape and recreate those connections and send them forward into the future. And that's what I mean by heritage work, this process of intergenerational connection that happens when we engage with things like language, knowledge, teachings, practices, etc. Heritage is not just a cultural thing either. We can also think about our disciplinary heritage as scientists, as researchers. At CCI, we have an interdisciplinary heritage. And so this is why I think that any of us, anytime that we engage in research, we are doing heritage work. We are engaging with those terminologies and methods and techniques in particular ways that will shape how future generations use those. And this then creates opportunities for us to engage in what I call critical heritage work, or not just me, it's called critical heritage work, which is a process of engaging in reflexive and focused ways, intentional ways that call out injustice, reclaim connections, and transform practices. In Indigenous communities, this might look like things like the repatriation of ancestors, the revitalization of language, and reclaiming of traditional practices. So I'll be doing this through I just wanted to encapsulate then what is my research question here. And that is, how can research and researchers participate in critical heritage work in the redressing of harms and the reclaiming of heritage with, for, and by Indigenous partners? And so, as I mentioned, I'll be doing this through a case study involving Wabanaki pottery heritage. The Wabanaki have a very rich and deep pottery heritage. It goes back about 3,000 years. They haven't been engaging in the crafting aspects of that heritage over the last several hundred years. And that means that a lot of the physical material tends to reside in the places in the materials that Wabanaki ancestors left behind that as scientists, we like to think of as archaeological sites.
And this includes the site of Holmes Point West in Machias Bay, which is where the University of Maine has been doing its archaeological field school since 2008. And that's been about every other year. So that's recovered a lot of cultural material, including a lot of pottery. And there hasn't yet been any kind of a comprehensive analysis of that pottery. So that's one reason that I'll be bringing that into this conversation. Machias Bay is also a Passamaquoddy place of spiritual continuity, and those field schools, in fact, arose out of an interest from the Wabanaki, or sorry, the Passamaquoddy tribe, in better understanding the ancestral relations to the place and how that might inform their work today. They have many projects oriented around strengthening their connections to Machias Bay, including some work with the petroglyph site at Birch Point, which I think Bonnie might have mentioned yesterday, but it's the largest grouping of petroglyphs in New England and perhaps even the Eastern Seaboard. So I'm actually missing a slide here, which was just to say that I'm entering this work using a community-based participatory research framework. So that's known as CBPR. And some of the key principles of CBPR are being engaged with the communities and treating them as partners throughout the research process, from developing research questions, including interpretation and then distribution of results. CBPR also involves an element of building capacity in communities to help them participate as equal partners in the process, and engaging in a spirit of reciprocity, making sure that everyone is benefiting from that work. So as I enter the CBPR part of this research, I've started to have some conversations with Donald Soktoma, who's the Passamaquoddy Tribal Historic Preservation Officer. And some of the things that I've heard him talking about are an interest in connections between the designs on potsherds from Holmes Point West and the petroglyphs at Birch Point, whether the potters at this place used local clays, if we can demonstrate that scientifically. He's interested in learning whether potters or pottery had connections to other places in the region, and generally in place-based relationships in Machias Bay. So as I consider these questions, I'm asking myself, what can I contribute to this as a researcher with a particular skill set? So again, my training is largely in archaeology. So from the archaeological site, we can look at the attributes of individual sherds to understand basically the story of those sherds. How were they made? What were the crafting technologies being used? And maybe even some information about the relationships that potters had with their community, with their teachers and such. We can also use radiocarbon dating to understand some of the temporal relationships. And as archaeologists, we can draw on the archaeological context and do spatial analysis to understand how pottery in the site relates to other material types and to cultural features in the site as a whole. I'm also trained in historical geography, and so able to come to this with place-based thinking and have some skills in mapping, in spatial analysis and GIS, and in communicating spatial data such as through cartography. And then I added on here materials testing, because this really speaks to that question about if they're using local clays. There's actually a clay source, a beautiful clay source that's maybe 50 yards from the site. But I don't have any training in it specifically. It's something I'll have to develop, but it is a possibility for this project. I'm gonna skip over that one, I think, but thinking back to the research project as a whole and that first research question I put forward, my methods in getting at that are going to be drawing on autoethnography, which is the use of personal experience to describe and interpret a cultural experience. So using journaling, self-interviews, potentially interviews with others about myself to consider my own positionality as a non-Indigenous researcher. What are my biases? What are my assumptions? And how are those implicated in and being shaped in the research process and in the research as cultural, as heritage work?
It's also going to involve a lot of a reflective piece, getting to that critical perspective on archaeological heritage, on the heritage of archaeology as a discipline, and how archaeological practices have served to erase Wabanaki pottery heritage, have served to kind of dispossess it and claim it as its own in the ways that we've treated and analyzed and talked about heritage in our own circles. But in terms of the community engaged piece, I just, this graphic kind of outlines some of the methods and techniques and things I'll be bringing into this work. So on the outside are some of those, my own scientific training that I'll be bringing in, but then hoping to interweave that through iterative engagements with community members around story work, around crafting, which I'll get to in a moment, actually crafting pots together. And also involving site visits, maybe community mapping and collaborative critique. I'm hoping to engage community members in those conversations about the harms that archaeological practices have caused and how we might change those going forward. So next steps for me, again, I've been having these early conversations with Donald Suktoma, and then this summer, I'm helping to organize a pottery workshop where we will host some Wabanaki community members and actually make and fire pots. And in that process, hope to have some conversations with them to get more on their particular questions and how we might start to shape those into a research project. So with that, I'd just like to thank my advisor, Dr. Bonnie Newsom, as well as my committee members, and Donald Suktoma, again, who's the Passamaquoddy Tribal Historic Preservation Officer, and my lab mates in the Northeast Archaeology Lab. Thank you. Yeah.
Curious if you have any of the journal prompts you referred to for the collection available and if you're willing to share them.
That's a very good question. I haven't gone through that process yet of coming up with journal prompts. I've started the journaling, but it's been pretty unfocused at this point. Yeah, thank you. That's a good question. Yeah, I'll be happy to share those when I have them. To check back in a month, I'll be defending my proposal mid-May. Yeah. All right, I know I'm all that's standing between you and lunch, so thank you very much.
All right, well, thank you very much for the opportunity to speak with the group today. And I've loved listening to all the presentations on ice and Arctic and subarctic things. And now I'm going to switch gears a bit and talk about forest ecology and carbon storage in trees and soils. So I'm up at the University of Maine at Fort Kent. Forestry and forest management are some of our big programs and interests. And specifically today, I'm going to showcase this study that I have on the title page, which is a manipulative field experiment designed to assess whether biochar, which I'll talk more about in a moment, whether biochar helps improve tree growth under drought stress conditions, and also whether biochar can be a suitable means of increasing soil carbon storage. And I make extensive use of the assistance of undergraduate students in these field projects. Got this great picture of Nick and Geraldo helping to fill pots with soil and char, and then also this portable soil respirometer for measuring respiration rates. So to delve in a little bit further, this is the background is we all are familiar with. Climate change is happening. There's a lot more extreme changes forecast for the future. This is likely to increase loss of carbon from soils, especially in Arctic, subarctic, and northern temperate forests. Biochar can be made from, it's typically made from wood or other plant material. Typically that's done through thermolysis. In other words, you take wood, you set it on fire, and then you reduce or exclude oxygen, you end up with charcoal that can be ground up into familiar powder, such as the one shown here in the bottom right. And that is currently being marketed and used as a soil amendment to improve water and nutrient retention in soil. It's also known to be highly resistant to oxidative losses, unlike a lot of the soil organic matter that we see in the Maine woods right now. So I'm also interested in seeing whether this material can help increase carbon storage when changing climate is tending to reduce that. So to test these questions about whether biochar can increase soil carbon storage and promote tree growth, I set up a manipulative field experiment here. This is a 3-year study financed primarily by the Maine Economic Improvement Fund, focused on developing forest management practices and also better quantifying the value of Maine's forests in terms of carbon storage, because whether you feel good about it or not, cap and trade is real, and selling and trading carbon credits is a way for commercial land managers to make money, or at least decrease loss of money. In this particular experiment, we've got 4 common Maine tree species. That includes white spruce, Norway spruce, which is increasingly being explored as a more climate tolerant species for reforestation, sugar maples, and balsam poplars. And this is broken down into a subset of comparison groups, including soil with and without biochar. We're looking at several different types of biochar, including a set of residues from biofuel production, which is something that resembles a bit more like sphagnum peat moss than actual charcoal. And then we're also going to, starting this year, include a moisture stress comparison group to see whether these soil additives can increase tolerance of trees to drought stress. So far, the data are very limited since we just set this experiment up last year. The first serious data that we collected is represented in this figure here. About 2 months after setting up the experiment in these pots, myself and a couple of students took the Lycor infrared gas analyzer with the soil respirometer, and we measured soil respiration rates, that is losses of CO2 from soil in the fall. And what we found, not surprisingly at all, is that the control pots that didn't have any added carbon lose less, and if you add carbon, you lose more. Also not surprisingly, these biofuel production residues, which have much more semblance to sphagnum peat moss than charcoal, you lose a bit more carbon. Now, I present this figure with a couple of caveats. One is that the timescale is relatively short. 2, this is using potted plants in freshly tilled soil. And it's pretty close to universal knowledge that when you till soil, you increase carbon loss. So the really exciting data are going to come this summer and next summer when we continue measuring soil respiration now that that soil has had a chance to settle. And also at the end of the experiment next year, where we do a SOC analysis and actually can do a mass balance for total carbon lost, and also include tree biomass in that model. So with that, I'd like to thank the many undergraduate students who have contributed to making this project possible, and not only the Maine Economic Improvement Fund, which helped sponsor the start of this project, but also JDI for donating the spruce trees, and the myriad NSF grants that I'm now PI or co-PI on, that is really helping expand more dimensions on this project. If I give a couple of concluding remarks, starting 2026, I'm going to be looking for more undergraduate students to come spend the summer in Fort Kent as interns and work on this and other projects. I'm also open to collaboration opportunities for expanding this and other projects where we have a framework and we have a system in place and doing more science with that existing infrastructure. Thank you very much.
Full time for questions, so call on anyone you'd like.
Go ahead.
If you have any ideas as to why this chemical oxidation derived biochar has more variability that might be creating that uncertainty now.
Yeah, that's a great point, and I noticed that as well. And notably, I simplified the statistics here. In magnitude, this is about 3 times this value, but these 3 don't end up being statistically different because of the big error bar. My hypothesis is that because that material is more, again, texturally and chemically is more like sphagnum peat moss, as opposed to a highly reduced carbon material. Trying to think of the best word there. Essentially, it's more chemically reactive. And given that the soil was recently amended and tilled, you're going to see a lot, I would expect to see a lot more variability. This year, I hypothesize that that variability is going to settle down now that that soil's had all winter to kind of mellow. But we may still see more losses for a while because, again, chemically, the combustion-derived chars are much more resistant to oxidation. Yes.
I'm confused though, if the biochar causes more loss of soil carbon, what's the advantage in that?
So here's the caveat, right? There is no advantage if it is consistently resulting in more losses. The caveat right now is the data I'm presenting here are for a limited snapshot in time. The goal of the project in the bigger sense is going to be to take at least 3 more rounds of these measurements this summer, 2 more rounds next summer, and then do a final carbon balance that includes plant plus soil. So we know how much is added, we know how much is lost. It's that net carbon gain, which I'm going to look at as being of higher importance than this single short-term snapshot.
But are you anticipating that after some years that the 3 right-hand bars will be smaller than one on the left?
Likely, yes. The other consideration is possibly they'll all become very small because this one just loses all of that added carbon. The reality is anytime you add a bunch of something, you're going to lose more of it. So in the bigger picture, it's about what's the total balance. If we added, in this case, it was 10% by volume char, so it's taking a soil that normally had about 3% carbon, it's now got about 13% carbon. So the fact that you're seeing a doubling of loss rates, which are relatively small compared to the total carbon added, needs to be put into context.
They're delaying the oxidation of the of the wood by stopping oxygenation during combustion and delaying it until you put it in the soil when it completes the combustion.
Right, but at a much slower rate. Whereas if you take typical organic carbons, so humic substances, things like peat moss and leaves, that's going to lose carbon a lot faster, especially in an exposed environment.
Thank you.
Do I have time to get your question real quick? Probably not. Okay. So,
All right, our next one is by James Fasthook, which is over Zoom. So we're gonna hope that this works and someone might need to play with the volume back there.
Can anyone hear me?
Oh,
Yes.
we're good then.
Okay. So I'm concerned with climate change on Mars. Mars, once upon a time, had rivers flowing on it, and this is back 3 billion years ago, but that's the time period that we're interested in, since that's the time period when Mars had a more clement climate. Now, there's a big controversy between the cold and icy early Mars and the wet and warm. One of the problems with the wet and warm early Mars is that at that time the sun was fainter than it is now, about 70% as bright as it is now. So it's very difficult, even with a lot of CO2 loading, to get an atmosphere that produces rain. But it's easy to get one that produces snow. And so we're looking at glaciers. In particular, we're looking at events that can release a lot of water quickly from a glacier, because we have these evidence of these big outburst floods, these river valleys that are carved, and their distribution seems to match up pretty well with where the ice sheets would be if we trust the climate models that we do for these early Mars situations. So one mechanism that we're looking at is what happens when lava flows out onto a glacier. And a couple of things happen. One, when you load the glacier with this rock layer, this increases the driving stress and you get a rapid acceleration. That rapid acceleration doesn't last very long, but then as the heat from the lava melts its way into the ice and warms the ice becomes softer, and so you get this secondary acceleration peak. All through this, the lava is melting a big hole in the ice that's filling with water. Some of it spills out onto the surface of the ice and runs down onto the adjacent land, but some of it can penetrate through crevasses to the bed, where it would add to this acceleration as it lubricates the bed. As kind of a secondary idea here, or a secondary function of this model, is we're looking at astrobiology. We're considering the possibility that life on Mars lived underneath the glaciers, as opposed to in a transient ocean. The ocean that they consider on Mars was a very short-lived thing, but there is the possibility that the water produced by the glaciers could be the biologic refugia. So that's this study, the effect of lava loading on an ice sheet, and the water that's produced by it, and the rate of discharge, and how much of it gets to the bed through moulins, and so forth. And I'll stop there.
Do questions over Zoom?
Sure. Yep, but they'll have to come up here to.
Okay,
so he can-
we have time for like one question, so if anyone has it, come on up here.
So you can be heard by Jim.
Not looking like we have any, so okay. Thank you.
Thank you.
I'm now very pleased to introduce our alumna lecturer, Rachel Fowler, who is a graduate of the Ecology and Environmental Sciences program here and the School of Biology and Ecology. She completed her PhD in 2019. She was a member of the Saros Lab and studied carbon cycling in lakes in Southwest Greenland, Maine, and Australia. In 2020, Rachel began work on the Second Century Stewardship Project that she will present today. And she also started in her current position as the Biology Lab Coordinator for Bio 100 and 200 labs here at UMaine. Rachel.
Thanks, Dan, and thanks for having me here today.
It's been exciting and inspiring hearing some of the talks that you've given over the past couple of days. And as Dan said, I am the Bio 100 and 200 lab coordinator. So some of you have been or are currently TAs with me, and maybe more of you will be in the future. So it's fun for me to be here and share some of the other work that I do. So as this is the UMaine Alumna Lecture, I thought I would tell you a little bit about my roots in CCI and talk a little bit about the journey from graduate school until the project that I'm presenting to you today and where I am now. So I got my master's in Boston. I studied marine carbon cycling. And after a couple of years of doing research cruises and getting sick on research cruises, I realized that I needed to make a change. So I moved back to Maine. I worked for a couple of years, and then the opportunity came up to apply to CCI's IGERT program, which was the Integrative Graduate Education and Research Traineeship. So I was accepted. I joined the Saros Lab, and I was really excited to start working on freshwater systems. So I joined the lab in 2014 and immediately joined an expedition to Kangerlussuaq, Greenland. And a big chunk of my PhD work was set here on lakes in Southwest Greenland. And I returned for every summer for a few years on expeditions. So here's a couple pictures from that work. On the left, you can see that we've acquired a sediment core from a lake and are getting the core ready to extrude. And on the right, I'm setting up a dust collecting instrument on the landscape. I also worked on lakes in Maine, primarily in Acadia National Park. From 2016 through the rest of my PhD until 2020, I was the Friends of Acadia aquatic scientist. I worked closely with Bill Golly, who is shown here. Bill is the former air and water quality lead at Acadia National Park, and he's recently retired. Bill is a co-author on the project that I'm going to share with you today, as is Jasmine Saros and fellow CCI alum Matt Farragher. So let's fast forward to April of 2019. This was a really exciting time for me. I defended my dissertation. That was great. You can see my 2019 Borns mini paper here. It was all polished. It was ready to go. And a couple days after I defended my dissertation, my daughter Tara arrived. So I didn't present my final Borns talk. So it feels really exciting and kind of full circle to come back this year. I always felt like I owed just maybe one more Borns talk to CCI. So this is Tara. She just turned 6. This is her last month tromping around Moosehead Lake. So at the end of 2019, I applied to and was accepted to the Second Century Stewardship Program through the Schoodic Institute at Acadia National Park. I received an award to examine the vulnerability of lakes in Acadia National Park to future harmful algal blooms. So Second Century Stewardship was a program that ran from 2016 to 2023. It was brought about by a partnership between the Park Service, National Park Foundation, AAAS, and the goals of this program were to advance conservation science in the parks and to expand on stewardship of cultural and natural resources. So this has since grown into the Acadia Science Fellowship, which you may have heard of. So work on this project was largely completed last year. Last year, we submitted the final report that was published in the National Park Service, and then the Park Science magazine highlighted this work in their features section at the beginning of this year. So before I dive into this project, what I'd like to do is set the stage and give you a little bit of context for how the project fits into ongoing science and historical science at Acadia National Park. So the next 3 slides come from the 2020 update of Maine's climate future, and I'm sure you're all familiar with these trends. So let's talk about temperature in Maine first. So average annual temperature has increased 3.2 degrees Fahrenheit in the last 120 plus years. And several of the warmest years on record in the state have occurred since the turn of the century, the 21st century. Precipitation in Maine is also changing. And this is looking like more rain and less snow. So average annual precipitation has increased almost 6 inches since 1895. And this is what that trend as less snow is looking like, kind of a longer, steadier, slower decline. This is a really cool figure that Bill Golly made a few years ago. So this figure depicts ice cover on Jordan Pond. You can see, so the bottom, the x-axis is date. And you can see when ice went on Jordan Pond and when it came off, and you can visualize really easily the duration from year to year. And I love how far this goes back. It might be hard for you to see, but this goes back all the way to the 1989-1990 season. The last few years are cut off from the top of the figure. They're not there. But what I'd like to share with you is that the 22-23 season and the 23-24 season both had relatively short ice cover duration on Jordan Pond. In contrast with this year, this was a pretty icy year. And I just heard from Kathleen Brown, who is the new air and water quality lead in Acadia. She took Bill's position, that ice off in Jordan Pond happened about a week ago. She said it was April 10th. So how do these climate change impacts affect lakes in Maine, lakes in Acadia National Park? So these are some of the things that we're thinking about. Changing water levels, so things like flooding or droughts, and impacts on drinking water, for example. Changes in temperature. So temperature, we'll talk more about a few slides from now, but temperature is important because warm water holds less oxygen than cold water. And that can be really tough on aquatic organisms. It can allow for spread of invasive species. It can promote algal growth. It can allow cyanobacteria to outcompete other types of algae. We're also thinking about increased runoff, so from the landscape into the lake. And this has implications for reduced water clarity, getting greater nutrient inputs, and also light, how much light can penetrate into the water column. So what's being done in Acadia to monitor water quality as this is going on? So there's a multifaceted approach, and I'll explain the different facets. So current monitoring. So during the ice-free season, there's monthly water quality monitoring of lakes in the park. This includes things like profiles of temperature, dissolved oxygen, pH, algae throughout the water column. Water samples are also taken from different depths in the water column and analyzed for parameters like nutrients, lake productivity, and other metrics. Water clarity is taken with a Secchi disc. Lake water level is measured. And then there's the high resolution monitoring. So since 2013, Jordan Pond has been instrumented with this high resolution data buoy each ice-free season, typically May to November. Maybe you have seen this if you've been in the park. So sensors are deployed in the water column, and you can see, let's see if this pointer works. This graphic shows you the setup under the water. So over 1,400 measurements are collected every day. Water temperature down to 16 meters depth, dissolved oxygen, light, pH, chlorophyll, among other metrics too. So let's take a look at the data that these different types of monitoring produce. So the top two figures are made from those monthly sampling excursions that I was talking about. So on the left, we have the Jordan Pond average surface layer temperature in the month of August. So the temperature of that epilimnion. And then on the right, we've got the depth of the epilimnion. And we can make these for various lakes in the park. And then we can compare that with those continuous data from the Jordan Pond buoy that give us these temperature plots, these annual temperature plots, which are the colorful figures on the bottom. And you can see that these high resolution measurements can convey a lot of information over space and time. So the high resolution data from the Jordan Pond buoy also can show us how precipitation links the landscape to the water quality of the lake. So on this summer day in 2023, the weather station at the Jordan Pond House recorded a precipitation event over 2.5 inches of rain. And almost immediately, the FDOM sensor, so fluorescent dissolved organic matter, on the Jordan Pond buoy recorded this pulse. And this is really important because dissolved organic matter can come from vegetation on the landscape, breaking down vegetation, and it can kind of give lakes this tea-stained color. And you can imagine that would be important for light penetration, temperature, nutrients in the lake. And finally, I want to talk about monitoring air quality, atmospheric deposition. This is monitored from a 10-meter tower in Acadia National Park. Air quality monitoring started in the park in the 1980s, and it has captured these declines that you can see in nitrate and sulfate in wet deposition, so acid rain. And I've circled in 1990. And you can see how after that time, both of these metrics have decreased. And this is resulting from the Clean Air Act amendments of 1990. And why does this matter for lakes? So we just talked about dissolved organic matter coming from the landscape to the lakes. So acid deposition can affect the transport of that organic matter from the landscape to the lakes. And when we have these big precipitation events, like the one I just showed you, for example, that can be really important. So as you've seen so far, Acadia National Park has a rich legacy of historical data collection and also over a decade of high frequency monitoring. So we built off these resources to create a risk assessment for different types of lakes in Acadia National Park to future harmful algal blooms, or HABs, as I'll be calling them. And you may have also heard them called cyanoHABs. So HABs, just to briefly define them, they can be smelly, unsightly blooms on the water. They can cause irritation to the skin, liver damage, neurological problems. They occur when toxic cyanobacteria are present at high concentrations on the water. And I want to point out that not all cyanobacteria produce toxins, and not all toxin-producing cyanobacteria produce toxins all the time under all conditions. So in recent years, over the last decade or so, lakes in Maine have been experiencing more and more HABs. They're occurring more frequently. Even in drinking water lakes, like Lake Auburn, for example, has been in the news, and in other systems that people might consider pristine. So we want to know, what does this mean for lakes in Acadia? So this figure illustrates some of the long-term data used in the project. So these have been collected in the park from the 1990s onward. Things like secchi depth, chlorophyll, nutrients. These are really useful metrics when considering which lakes might be vulnerable to HABs. And I just want to take a moment to give a shout out to Matt Farragher, because all the sampling for this project was done in the spring, summer, and fall of 2020. COVID was raging, and Matt was able to organize most of the sampling, and he also made several of the figures that I'm going to show you today. I'd like to introduce you to our study lakes. So we focused the study on 3 lakes. These are representative of other lake types in Acadia National Park. So Jordan Pond, here on the bottom left, I've talked about a little bit already. Jordan Pond is oligotrophic. It has low nutrients. It's very, very deep, and it's also really clear. And then we have Seal Cove Pond. Seal Cove Pond is more mesotrophic, higher nutrient levels. It's not as clear. It's shallower than Jordan Pond. And Seal Cove Pond is unique among this group in that it's not entirely within the boundary of Acadia National Park. There's residential development and a road on one side. And then kind of at the other end of the spectrum, we have Witch Hole Pond. This is more meso-eutrophic. It's a shallower lake, and it's not nearly as clear. So for each lake, we collected temperature and dissolved oxygen data continuously. So throughout the entire ice-free season, we had a buoy out in each of these 3 lakes. And near the surface, about 2 or 3 meters below the surface, we had temperature and dissolved oxygen loggers. And then we had another one down near the bottom of the lake, or in the case of Jordan Pond, which is very deep, about 30 meters deep. So we collected those continuous dissolved oxygen and temperature data at the 2 depths, and then biweekly sampling was done throughout the water column for metrics like nutrients, chlorophyll, counts of different groups of algae. We also measured phycocyanin. So phycocyanin is a pigment, and it's indicative of cyanobacterial concentration in lakes. We can't tell you if they're toxic or not, though. So for the next couple of slides, I'm going to show you some figures that look like this. On the top trio, we have data from those continuous measurements at the 2 depths. And then in the bottom, we have data that were interpolated from those biweekly water column sampling events at 1 meter intervals. So these are temperature results from each of the 3 lakes during the 2020 season. The first column is Jordan Pond, and then Seal Cove Pond, and then Witch Hole Pond. So what I would like you to take away from this figure is that Jordan Pond was very different from the other 2 lakes. So temperature is really important, because at prolonged temperatures of greater than 25 degrees C, some cyanobacteria can outcompete other algal groups. So here you can see that if we look at the top left figure, the surface water of Jordan Pond never quite even reached 25 degrees C during the summer of 2020. I think the max temperature was 24.9. And then we can contrast that to the other two lakes, which had temperatures greater than 25 degrees C for several weeks during the summer season and even into the fall. I think their max temperatures were more like 28.1 and 28.9 respectively. And this is the dissolved oxygen story. So again, we can see Jordan Pond, dissolved oxygen in Jordan Pond is behaving very differently from the other two lakes. So the bottom water of Seal Cove Pond and Witch Hole Pond became anoxic in both lakes during the summer of 2020 for several weeks, especially in Witch Hole Pond. So I already mentioned that warm water holds less oxygen than cold water. These conditions are hard on aquatic life, but this matters for another reason too, and that's because of chemistry. So under anoxic conditions, lake sediments, depending on their ratios of aluminum to phosphorus and aluminum to iron, can release phosphorus into the water column. This can fuel algal growth and cyanobacteria in particular. So we don't have the sediment chemistry of Witch Hole Pond, but we think this might be what's happening in this lake, or maybe this happened during 2020. And I'll show you why. And I also want to show you that Jordan Pond did not get anywhere near anoxic during the summer of 2020. So let's take a look at the phycocyanin data, which is that indicator of cyanobacteria. So it was detected at the surface of Jordan Pond and Seal Cove Pond after ice out and kind of intermittently throughout the rest of the season. And then on this discrete date toward the end of the summer in Jordan Pond. And then Witch Hole Pond, we see something different. We're not seeing so much on the surface, but we're seeing more throughout the water column, particularly in the summer and into the fall. So we think that could be supporting our hypothesis that those warmer water conditions with lower dissolved oxygen might be affecting the sediment chemistry and potentially supplementing nutrients into the water column that are supporting cyanobacteria. So in those previous slides, I showed you some differences among the water quality parameters, temperature, dissolved oxygen, phycocyanin for the 3 study lakes. Building on those findings, so this is kind of the second step of the project, we developed a scorecard to assess the individual risk of all lakes in Acadia National Park to have formation based on morphometric and water quality characteristics of each lake. So to develop the risk assessment scorecard, we included parameters that have been shown to affect vulnerability to HABs from the literature and for values that are known for lakes in Acadia. So things like trophic status. Is it oligotrophic? Is it more mesotrophic? Flushing rate. What's the residence time of water in the lake? What's the morphometry like? How deep is the lake? Does it stratify? And is it completely within the boundary of the park? How protected is it from external inputs? So we weighted these parameters based on their relative importance in HAB development, and then categorize those resulting ranks into risk levels of low, moderate, or more considerable. And this is the risk assessment scorecard. So on the x-axis, we've got the lakes in Acadia National Park. On the y-axis is that index of risk. And the lakes in green are at a lower risk, we believe, of future HAB development based on their morphometric water quality characteristics. And you'll see that Jordan Pond is included in that group. The lakes in yellow we think are at more moderate risk. Seal Cove Pond is in that group. And then the lakes in orange, we think have more risk factors and are more vulnerable to future HABs. And Witch Hole Pond is in that group. And you can see that some of the circles are outlined by a black ring, and that indicates that those are drinking water sources. So 4 of the drinking water sources are in that green category and 2 are in yellow. So this scorecard supports our previous findings based on the water quality sampling that we did, that lakes like Jordan Pond that have a lot of characteristics that are similar to Jordan Pond have fewer risk factors to future HAB development, while lakes like Witch Hole Pond have more risk factors and might be more vulnerable to developing HABs in the future. So the next step is using these results to support management of lakes in Acadia National Park. So the Park Service uses an approach to climate change adaptation, kind of a decision approach called the RAD framework in some of their decisions. And this is what the framework looks like. And RAD stands for resist, accept, and direct. So working with resource managers at the park, we can kind of think through this decision tree for management responses to climate change in the Acadia Lakes. So if you start at the top of this decision tree, you ask yourself, are you shaping the trajectory of change? If you're not, you're going to do actions within that accept framework. That doesn't mean that you don't do anything or you just keep doing the same thing over and over. But there are ways that you can maximize what you're doing. If the answer to that question is yes, you're shaping the trajectory of change, you go to the next question. Are you managing for historical conditions or a new desired condition? If it's a new condition, you're going to be directing the change. If your answer is historical conditions, you're going to be doing actions to resist the change. So an example of this, thinking about lakes and harmful algal blooms, would be aerating the lake, trying to break up stratification, or maybe adding algicides to the lake. So because currently we don't think there are problems with HABs in Acadia National Park, our decision will likely be within the realm of accept and actions related to accept. So since 2021, scientists in the Air and Water Quality Program have been contributing data to nationwide programs for cyanobacteria monitoring, these collaborative programs. And they've started doing some cyanotoxin tracking and quantitative PCR in a few of the lakes. So I've been talking some with Kathleen Brown at the Park Service about what these actions mean specifically for management of Acadia Lakes. And what are some ideas that we've come up with are doing more winter monitoring, more under ice monitoring, increasing spatial resolution of monitoring, trying to do some more with high frequency sensors in the lakes, expanding that cyanobacteria ID and toxin analysis to figure out what's actually in the lakes. Are there toxins? What's present? And then we also think it would be really useful to set up a system of alerts for exceedances of some of those key water quality parameters that I was talking about. So say an alert goes off after a water quality parameter has exceeded some threshold, and that could trigger additional sampling, additional monitoring to try to figure out what is going on. And you can think really carefully about how to spread monitoring resources out among different lakes, thinking about cultural, natural value of the lakes to the park, to the state of Maine, and also how at risk are different lakes. And then finally, thinking about opportunities for partnering with local groups and stakeholders and getting kind of amplifying community engagement and awareness of what could happen in the future. So we're planning a talk for the fall to kind of explore some of these ideas. So stay tuned for that. And I want to take a moment to thank you all for having me here today, and also to thank the supporters of the project, funders, people involved in the project in so many capacities, several of whom were fellow EES and CCI alum. So thank you.
And we do have some time for questions, so if you want to call in anybody who raises their hand, that would be great.
Sure.
We have questions.
Great talk, thanks so much. How similar do you think things would be if you chose a different oligotrophic lake, unlike Jordan Pond, which is very different morphology from the two lakes?
Mm-hmm. Yeah, that's a great question. I think that this is the tricky part of, having the resources to pick 3 lakes in the park and try to pick 3 that are kind of representative of different lake types. And there's a lot of things, a lot of metrics that are similar to other lakes and a lot that are pretty different from other lakes. So I think this kind of falls into that, how do I go back? This kind of to-do list for expanding monitoring spatially, like to other lakes, to say, is this as true as we think it could be for different lakes?
Other questions? Yeah, great.
When it comes to the RAD framework, and it's either resist or direct, do you know if it's a case by case on which you would choose, or is it more based on how cost effective one method would be versus the other?
So I think it's case by case, and I think it depends on desired outcomes and what's most important to the individual unit, so the individual park and the stakeholders in that area. I think there are cases where some people want to keep a system exactly as it is forever and ever and ever, and it's just a case by case basis. Another one over here.
And then in Jordan Pond, there was like the one discrete day that you had pointed out, like through the water conference, like there was like an event. I'm curious, like, what you would like is behind that, or like why that appeared in one day.
I don't know. Oh, I just passed it. Yeah, it's an anomaly. So I think that occurred in an area of the water column where there probably was a lot of primary productivity going on. It's toward the end of the summer, so the lake is pretty stratified. It's pretty warm. I think at that depth in the lake, the cyanos aren't getting too much light. They're getting just the right amount of light to do their thing. But it's interesting how it's just kind of that discrete day of sampling, and how we don't see that so much in Seal Cove Pond, for example. Yeah. And then George and the neighbor. George, you want to go first?
Don't you think you should add sediment cores from each of the 3 lakes and reconstruct their entire past history?
Yes.
Well, I mean, I'm facetious a little bit, but even short course would give a lot of information about the variability in recent centuries. But I'm thinking about Sergeant Mountain Pond, which was studied a few years ago, and actually a long-term reconstruction of the water chemistry in relation to changing environmental conditions. And it made me think that it would be interesting to think about things in those timescales a little bit, as opposed to just a few years of sampling. I realize you're stuck, you have what you have, but we all around here, we think in longer timescales, as you know.
Oh, absolutely. I totally agree. So I'm passing the torch to Avery.
Don't pass me.
What?
But
I know. Not all of them, but Seal Cove Pond. I did course. So I have a paper on it. Seal Cove Pond versus Jordan Pond. Yeah, that was a chapter of my dissertation.
did
Avery.
you include phycocyanin or chlorophyll A in your metrics in scorecard at all?
No, we included, which direction am I going? So these are the 5.
Okay, I'll just call it morphological or chemical indicators. Why did you not include something that was more biological?
Because these were the things that kept coming up in the literature. And yeah, so we looked at, so the first part was kind of doing like the water sampling, water quality sampling to say what's going on biologically and chemically in the lakes, and then to kind of be able to classify the different types of lakes. And then we looked in the literature to develop our scorecard, and these were the big things that kept coming up as most important for HAB vulnerability. Yes.
Yes, got one more, make it the last question, I guess.
Sorry, I'm not even taking notes, so I missed it. I saw you had connectivity listed in earlier. What's the range of connectivity values for Lakewide?
I don't remember. Can somebody help me out? Yeah.
Thank you very much.
Thanks, everybody.
Okay, we just have a couple of more events. But before we go on to the next part, there are plenty of people to thank for the Bourne Symposium. There are 2 people that we have all interacted with, who are not only extremely important for the Bourne Symposium, but for every single thing that we do in the Institute. So I'm going to turn this over to Emily to say a little bit about them and show how much, in particular, the graduate students appreciate them.
Why don't you two come on up? I think you know who we're talking about.
I
think everyone knows how much the both of you do for all of us at all hours of the day. So we wanted to just get you a couple of some flowers, and then each of you, I don't remember which one's on top. Betty and Becky, a couple of gift cards, so you can just go have a nice meal and enjoy some time. Thank you.
Okay, now we have 2 more events. The next one is the official Climate Change Institute concert.
Could you fix this so that I'm being recorded with a neutral background?
Your face.
Yeah, just me.
Yep,
Thank you.
we can do that.
You want to be recorded?
They always do. Yes,
There you
I
go.
also send the text and it
So
gets
you are,
posted.
they'll see you right there.
All right. So hi, everybody. Those who has not been here for a punning summary before? Anybody? All right, well, you're in for something different. I've been taking notes on every one of the graduate student presentations, and I'll summarize them all. This is going to take a bit. I've got about 5 pages, so I think I had a lot of coffee this time, both yesterday and today. So I'm just going to get started. So I'm starting with yesterday's. I'm going to go in the order in which they were delivered. Eric Brown spoke on thermal windows in the southern flying squirrel and addressed a hot topic. His wide-ranging results might fly in the face of earlier thinking, but give us a window into how squirrels maintain their balance in the face of stress, temperature stress, that is. We're talking about about their behavior and not about squirrel psychology. And we're going to come back to some psychological issues later. So Tricia Hall Collins spoke on a glacial chronology from Lisa Ford, southwestern Norway, evidence for a cold reversal during the termination of the last ice age. Tricia gave a cool talk on the end days, that is, the end days of the last ice age. Her erratic research overrides prior results and suggests that the cold reversal was a global signal. And I'm sure there will be a robust back and forth on this suggestion about the reversal. Avery Lamb spoke on using paleolimnological approaches to disentangle the long-term nutrient and climate drivers of harmful cyanobacterial blooms. She considered the role of temperature and nutrients in causing these blooms and gave us food for thought about what will happen to cyanobacteria under climate change in Maine lakes. Her use of pigments associated with the two target species of cyanobacteria colored our understanding of the temperature and nutrient effects on these species and gave us a good picture of these relationships. Marina Miles spoke on and she changed her title, a cosmogenic nuclide record for Katahdin, Maine, USA. Marina advanced our understanding of the conflict between records of meltwater and temperature during Heinrich events. She suggested things ran hot and cold, that is, seasonally, as a reconciling hypothesis. She took a bolder approach to testing this idea by dating moraines at the base of Katahdin, but her results don't quite ice the answer. Sam Baumgartner spoke on Allen Hill's Antarctica climate shift indicated by water isotopes, dust, and iron. Sam spoke about studies on blue ice, which is old and cold, but paradoxically is happily easy to access the older ice. In several labs, she ironed out the record of dust, water isotopes, and Fe in a core from the blue ice. The results are still hard to determine in terms of the cause for a visible shift in the record, so we'll have to wait and see. Aaron Victor spoke on aligning circularity and climate reduction goals on packaging EPR schemes. Aaron offered a new definition of circular reasoning that exemplifies the dictum, waste not, want not. We can reduce climate change by enhancing the circular economy. Aaron notes a consensus in her survey that there needs to be a common signal on appropriate packaging. And perhaps it would get out to more people if they use Signal to propagate this information. However, there needs to be more study on which design would be more environmentally appropriate. We can't just recycle the same old ideas. Anna Treba spoke on possible teleconnection between the January 2022 Tonga eruption and climate extremes observed in 2023. Anna tackled an explosive topic relating to a volcanic eruption and seeing how it coordinates with recent climate change. Her results on the role of the aqueous ejecta are enough to give one vapors. I have to admit that I had a childish interest in seeing La Nina and El Nino implicated. Renee Clavette spoke on liquid water distribution within and beneath temperate ice on the Juneau Icefield, Alaska. Renee pooled knowledge on water beneath the Juneau Icefield in a case study that was tempered by factors such as the 3D, 2D, 3D nature of radar transmission, reception, and interpretation. Nevertheless, this approach wasn't all wet. She probably did find water and will test this result in a core next summer. Along the way, though, Renee spaced out and discussed Jupiter. As an aside, I actually seen, for those, and this will become apparent to those of you who are familiar with Greek mythology, a connection between Juno and Jupiter. All right. Matilda Borch spoke on the transition of marine terminating glaciers to land under a warming climate, implications for driving stress. Matilda discussed how sea glaciers end up getting beached and how they behave under stress. Perhaps there is a new field to be invented of ice psych. And we'll hear about that some more. We also heard how the transition from marine to land terminating glaciers kills fjords. Finally, she told us how hot films can be explosive, and that is not what you're thinking. Corey Limburger spoke on spatial distribution of trace metal chemistry in saline surface water in West Greenland. Corey tackled a salty topic that tested his mettle as a researcher, studying what is melting out of the Greenland ice sheet. He addressed the seeming paradox that as ice sheets shrink, toxic pollution grows. One could ask if glaciers are poison pills, but that idea may be all well. Amanda Gavin did not speak, and this shows that even if you don't show up, if you put in a title, you're going to get punned on. So she did not speak on multiscalar approach towards a holistic understanding of lake level in an agricultural, drought-prone subarctic landscape, but I'm sure she would have done her level best to grow our knowledge of lake behavior in an agricultural subarctic landscape, had she spoken. Kaylin Manello spoke on spatial and temporal variability in density and liquid water content in wet fern on Juneau Icefield, Alaska. That's quite a title. Kaylee talked about ice water, or how water damps down the fern on the Juneau Icefield. She saturated her talk with discussion of GPR techniques for studying water content of fern. She also raised our hopes by suggesting that fern water might mitigate the impact of glacial melting on sea level. To end up with yesterday's talks, Pratima Pahadi spoke on the impact of temperature and precipitation on growth and survival of tree seedlings, a comparative analysis of conifer and deciduous species. Pratima took our understanding of climate impacts on tree seedlings a fur piece. She branched out to discuss assisted migration, another hot topic as climate changes faster than plants can adapt or mitigate, or migrate rather. Pratima's experimental treatment of seedling growth shed light on the relation of temperature and precipitation to tree survival. She found that for most species, surprisingly, rising temperatures bite is worse than its bark. Moving to today, Emily Blackwood spoke on sightseeing archaeological features on the north coast of Peru. Emily discussed new dimensions in archaeological research. She has been turning the Ostra collecting station site into a site for sore eyes. Emily also explained about the slingstone piles, which might be the earliest evidence in the Americas of people getting stoned, among other pearls of wisdom that she showed us. Thomas Grindle spoke on how do lakes in West Greenland recover from abrupt lake browning following a compound climate extreme event. Thomas's interest in compound events, led to hypotheses about lakes that suffer brownouts. Given that this was the result of heat extremes, it's rather like New York City's brownouts. Thomas also explained that surface flow across the lie of the land helped give the lie to the term permafrost by melting it. This is not a cool finding. He still has some issues to iron out in understanding how the browning will progress in the future. Sarah Thomas spoke on geochronological record of ice extent during the Antarctic cold reversal at Bahia Penhot, Chile. Sarah covered the big chill in Chile, doggedly pursuing the timing of ice events during the Antarctic cold reversal to assess the causes for this event. Like online courses, the ACR may have been either synchronous or asynchronous. She concludes that it was the former, which is a switch from prior ideas. Given the focus on ice behavior, I have to return to the concept of ice psych, particularly considering that one of the hypotheses is about the bipolar seesaw. Kelly Hooper spoke on using geophysical survey to reveal patterns in monumental construction at Los Morteros, Peru, and that site name translates to the mortars. And in her work at the mortars site, Kelly is grinding away on her analysis of monumental anthropogenic construction. She faces and overcomes the difficulties on seeing through sand with GPR and comes up with several grains of wisdom about the nature and extent of sand-mantled architecture. Unlike the Ostra collecting station reported by Emily, with preparations to repel an invasion, Kelly's work is non-invasive. Megan Spoth spoke on Cordillera Darwin icefield extent during the last termination. Megan's work in the Cordillera Darwin is evolving nicely. Darwin. She is trying to explain the end times of the last termination that we've already heard about, a term that on the face of it seems both a bit redundant, last termination, and also rather chilling. nobody wants to be terminated. Like other dedicated CCI students, Megan is doggedly pursuing her research, in this case at multiple sites along the, wait for it, Beagle Channel. Catherine Westbrook spoke on the interhemispheric comparison of the late glacial climate reversal. Catherine has studied the LG climate reversal backward and forward. Despite using dates on erratics, her chronology is actually quite coherent. Her camel plot, which appropriately has 2 humps, it's not a dromedary plot, shows that New Zealand and Norway operated synchronously through the reversal. Alexander Roman spoke on Little Ice Age glacial advances found in the southern Alps of New Zealand at 43 degrees south, suggesting a global extent. Xander's reconstruction of Little Ice Age advances is no small feat. It's the Little Ice Age. He worked on dating moraines in New Zealand, where he had an intense experience, and he shows a picture of one of those tents. Xander asks if the LIA was a global event, and his world-shattering conclusion is that it was coincidental, but not a mere coincidence. Tahi Wiggins spoke on surface water dynamics at Echo Glacier, Lingit Ani. I was echoing. All right. Tahi used her Born's talk to bounce some ideas off CCI members about how surface water behaves at Echo Glacier and the role of liquid water in ice dynamics. She used surface water to get more insight into water throughout the glaciers. This is not just a superficial study. Peaking at peak lake size, she found that it is the result of drainage date rather than environmental variability. I note that in her image of radar data of water in the snowpack, she was careful to layer the lower margin as WT bottom instead of WT foundation. And I'll just give you a second to think about it. All right. Olivia Olson spoke on birdsong, multivocality in human-bird relationships during the ceramic period in Wabanaki homeland, a case study at Fraser Point, ME 44-49, ACAT 00110, Scudic Peninsula, Maine. And this, along with many topics, reminds me of a critique that one of my advisors, who was a geologist, Art Bloom, used to make of my titles for talks and papers, that they were basically abstracts in a title. Not a bad thing. So she's talking about various things at Fraser Point. And Olivia gave a notable talk in which she makes no bones about her interest in using an indigenous archaeology approach to faunal remains at Fraser Point. Although the site is too recent to have fluted points, and that's for the archaeologists here. It does have a bone flute that led Olivia to sound out other flutes from the Northeast in a comparative study that could be instrumental in improving our understanding of the meaning of birds and music among Wabanaki people. Mari Fromstein spoke on comparing measured and modeled glacier ice thicknesses using in situ ground penetrating radar measurements on Jarvis Glacier, Eastern Alaska. Mari presented a penetrating analysis of East Alaskan ice, comparing modeling with radar results. Given the uncertainties in the modeling, the radar data can't be waved off. Her deep dive into ice depth is reminiscent of what anthropologists call thick description. Mari made a significant find about model versus measured by profile type. And she saw that was different if you were doing horizontal or longitudinal. Along with other indicators that we need a field of ice psych, it turns out that we need to do behavioral profiling. Bailey McLaughlin spoke on Through the ST Ages, by the way, the best punning title. The realized climatic niche of US trees is conserved across life history. By analyzing life history in a climatic context, Bailey sees the forest and the trees, which would be in a jam if they couldn't conserve their realized climate niche. She asked what happens when climatic parameters change during a tree's lifespan and found out that juveniles have more limited tolerances than adults. And any of you who are parents will recognize this as something familiar. And it also raises the question of whether a climate change during early growth would create arboreal juvenile delinquents. Despite being a niche study, Bailey's results have broad implications. Roisin Rumsey spoke on analyzing bubbles in hyperspectral images of ice cores. Roisin uncorked a stream of data in her analysis of bubbles in ice core imagery. Her hyperspectral system gathers so much information that it is possible to do brute force, BRUT force analyses of the data. She even has the bubbles popping out of her images. So multiple dimensions of bubbles could be interpreted. All right, last page. Ali Berry spoke on the influence of fjord dynamics on iceberg distributions in Northwest Greenland. Ali explained how icebergs behave when under the influence of fjord dynamics, that is. She floated some thoughts on the unmodeled importance of icebergs in the climate system with a focus on what happens in Northwest Greenland. The effects of icebergs on fresh water input into the ocean is likely much bigger than recognized, perhaps even titanic. The problem is mainly driven by big bergs, which may sound like Sesame Street, but is really a matter of great concern. Leonardo Villacis spoke on capturing terminal and spatial dynamics of diatoms in Crawford Pond, northern Maine, for ground truthing stratigraphic records involving Alcacera. Leo is working out the bugs in diatom dynamics in northern Maine. Alcacera comes in large and small versions, and Leo found that size matters in response to ecological conditions. His work on the small bugs to understanding changing climate offered food for thought, and quite literally on the screen and right before lunch, which was cruel. Andrea Terrell spoke on a natural experiment from the Alpine to the Arctic, evaluating local adaptation in herbarium species using spectroscopy. Andrea discussed what happens when plants get high. Latitudinally and altitudinally, but not attitudinally. That would be a different kind of high. She planted the idea that herbaria collections leave open the possibility of long-term data to assess local adaptation. Andrea is pressing them into service in her project. She uses a non-destructive measurement system, but there are mitigating factors in this work, such as whether some specimens have aged out of utility and perished of thought. Finally, Elizabeth Rogers spoke on research as heritage work, a participatory action case study of Wabanaki pottery traditions. Elizabeth offered a novel, engaging perspective on Wabanaki ceramic traditions. This was no potted talk. She argued that archaeologists and other heritage specialists need to temper their research approach by privileging Indigenous participation and perspectives at every stage. Elizabeth is clearly and appropriately fired up about doing this work. Thank you all.
Well, thank you, Dan. Dan does this how many years now?
This is the third year where I do every talk.
Okay. Now, you all think that most people have been here for the entire 2 days, and you think that you were concentrating on what was going on. Just imagine what was going on in Dan's head. So, yes. Just a couple of comments about somebody who's a punster in this particular case, Dan. I thought that your overview was very pungent. And I also thought that in some cases it was rather punishing. So we're at the final stage of the Born Symposium for this year. It was fantastic, as always. Wish everybody a fantastic rest of the semester, summer season. Look forward to seeing all of you who aren't going to graduate, of which there are many actually, at the Icebreaker. This is the time when we have some awards. Every single person deserves an award for what they've done. There are a lot of different ways in which this has been judged. I have the pleasure of giving out the awards. They are for the poster session, for the presentation, and also the Churchill award. So I'll start with the poster awards. And if you would be so good as to come up and receive your award, I will pass it to you. So we have two number 3s for the best poster award. The first number 3 is Miranda Sykes. And the other first number 3 is Claudia de Camillis. Not here. Would somebody else like it? Okay, we'll wait. The second place for the best poster is Elijah Bradshaw. And the first place is Caitlin Johnson. Now for the presentations to third places again. The first third place is Olivia Olson. The other first third place is Catherine Westbrook. The second place is Leonardo Vilakis. And the first place is Mathilde Borsch. And the award for the Churchill Award for Outstanding Exploration goes to Emily Blackwood. I think there are pictures that are going to be taken.